Without objection, the chair is authorized to declare research at any time. Before I deliver my opening remarks, I wanted to note today that the committee is meeting virtually. I want to announce a couple of reminders to members about the conduct of this hearing. First, members should keep their video feed on as long as they are present in the meeting. Members are responsible for their own microphones. Please also keep your microphones muted until you are speaking. And finally, if members have documents they wish to submit for the record, please email them to the committee clerk, whose email address was circulated prior to the hearing. Welcome to today's hearing, and welcome to our distinguished panel of witnesses. I look forward to hearing your insights on how we can ensure the United States leadership in microelectronics. It wasn't news to the experts, but the last 2 years have brought into full public view the vulnerabilities in our microelectronics supply chains. Chips operate almost every piece of technology in our lives, from cell phones to cars. They are essential to our national security. Yet, the U.S. share of global semiconductor manufacturing decreased from 37% in 1990 to just 12% today. Hindsight allows us to see that our government and industry suffered a collective failure of imagination when we thought we could offshore our chips manufacturing capacity without consequences. Today, a single chip might go 1,000 production steps in 70 countries before reaching its final product. It took a global pandemic to expose the weaknesses of that approach. But we should not be fooled that this is a once in 100-year problem. Fortunately, the semiconductor industry still leads the world in research and innovation. In 1954, the very first commercial silicon transistor was developed by Gordon Till at Texas Instruments in Dallas, Texas. In 1958, Jack Kilby of TI invented the integrated circuit. And ever since then, because of investments by both the U.S. government and industry, we've continued to lead in microelectronics innovation. However, chronic technology and approaching certain physical limits, long-term growth will require breakthroughs in everything from fundamental material science to manufacturing processes. In the meantime, other countries are stepping up their investments. In particular, China is already outspending the United States to bolster its domestic semiconductor capacity. Moreover, they're investing in research and innovation like they never did before. They no longer want to just manufacture yesterday's chip. They want to lead in innovating tomorrow's chip. That poses both an economic and national security risk to us. To help maintain U.S. competitiveness in microelectronics, Congress passed the Chips for America Act. The CHIPS Act would make substantial investments in the future of semiconductor R&D. The act also includes incentives to bring semiconductor manufacturing back to our shores. I support full funding for the CHIPS Act. However, a one-time infusion of funding will not be enough to maintain U.S. leadership in microelectronics innovation. Advancing U.S. leadership in microelectronics will require a long-term, whole-of-government strategy. While incentives to reshore capacity now are important, The future will be shaped by now. We invest in innovation and the technical workforce. That is what we know and do best in this committee. The Science, Space, and Technology Committee is ready to work with the administration, industry, and the research community to oversee the implementation of the CHIPS Act. In addition, we will continue to explore opportunities to strengthen and expand our investments in microelectronics research, including at the Department of Energy. This hearing is the beginning of a long-term effort by our committee. I thank you to the expert witnesses that are here today, and I look forward to the discussion. The chair now recognizes Mr. Lucas for his opening statement.
Thank you, Chairwoman Johnson, for holding this morning's hearing. Every American who's tried to buy a car, tractor, or even a refrigerator lately knows that we're facing severe supply chain shortages. In many cases, these shortages are being driven by global disruption to the supply chain for semiconductors, or chips as many of us refer to them. Microelectronics, the devices made from semiconductor materials, are critical to how we live and work. They power our phones, make our cars safer, our homes smarter, and help us store and protect virtual information that is oh so vital to us. They are not only essential to our economic security, but our national security as well. The Chinese Communist Party has made it clear that it wants to dominate the globe in key technology areas. And part of their technology strategy is to increase China's share of semiconductor market through both investment and acquisition. U.S. technology companies obtain as much as 90% of their semiconductor chips from Taiwan, a huge risk given the geopolitical situation in the region. Microelectronics are necessary for the technologies of the future. Harnessing new applications such as artificial intelligence, 5G, and quantum sciences will require fundamental breakthroughs in microelectronic technology. While the factors that led to today's chip shortage are worthy of their own examination, our focus today is forward-looking. How do we secure America's leadership in advanced chip design? How do we regain our leadership in semiconductor manufacturing? We must answer these questions to ensure we never face a chip shortage or disruption in the United States again. Congress took the first steps to address this issue last year by passing the CHIPS for America Act as a part of the FY21 National Defense Authorization Act. The CHIPS Act, which when introduced was referred solely to the Science Committee for jurisdiction, authorized programs to advance U.S. research and development, promote industry, government partnerships, and incentivize domestic fabrication of chips. Today's hearing should provide critical guidance as Congress and the administration consider how to implement and fund the CHIPS Act. I have no doubt this will be a major legislative and oversight priority for our committee for years to come. To lead and advance microelectronics, the United States will need to make strategic investments along the entire innovation pipeline, from fundamental research and education to design to manufacturing. The federal government has a long tradition of investing in fundamental research for microelectronics, including through academic research institutions and federal laboratories. They're supported by the National Science Foundation, the Department of Energy, and the National Institute for Standards and Technology. Dr. Witherell will help tell us about how DOE and its laboratories have worked with industry and academia to drive scientific advancements in areas such as material science, energy efficiency, and novel devices. Access to materials, including critical minerals, chemicals, and gases, will be the key to increasing domestic technology production. Unfortunately, the U.S. has limited quantities of many of these critical materials, so research into alternative and manufactured materials could be the answer to domestically produced advanced semiconductors. Another challenge, which the CHIP Act takes steps to address, is advanced packaging. Experts believe that breakthroughs in packaging will be key to improving chip efficiency beyond the regular doubling of computing capacities predicted by Moore's Law. I look forward to hearing from our witnesses today about what will make a national advanced packaging manufacturing program successful. Developing a strong workforce in the United States to support the microelectronics industry is another challenge we need to solve. In the next 5 years, companies estimate that we'll need at least 42,000 semiconductor engineers nationwide. That demand is even higher for the full spectrum of workers needed, from skilled technicians and operators with associate degrees to those with advanced degrees. I hope our witnesses will provide some recommendations on how we can build this workforce. As Congress looks to strengthen U.S. chip manufacturing and advance our competitiveness in microelectronics, we must look to lessons from the past. We've been here before. In the 1980s, the federal government took strong actions to combat Japan's dominance in microelectronics. They included establishing a research consortium to support U.S. competitiveness in semiconductor technology, also known as Semitech. This government-industry partnership lasted until 1994. It helped the U.S. regain the lead for a time, but competing industry interests, waning government support, and other factors led to a decline that has put us where we are today. During this time, IMEC was also established and is still in operation today. IMEC has created an international ecosystem for more than 600 world-leading industry partners and a global academic network focused on developing and testing cutting-edge semiconductor innovations. I know several of our witnesses have worked with both consortiums, and I look forward to hear what lessons can be taken from each and used to inform the establishment of a National Semiconductor Technology Center and the Department of Defense's Microelectronics Commons. In closing, I'd like to note that yesterday marked 2 weeks since the Democratic leaders of the House and the Senate announced that there would be a conference on the Senate-passed U.S. Innovation and Competition Act and the innovation bills that our committee carefully crafted and passed in a bipartisan basis. Unfortunately, we're still waiting on the details of that conference. Chairwoman Johnson and I are ready to go. We've been ready to go for months. It's time for leadership to move forward on a bipartisan conference of all the committees of jurisdiction. The Senate bill will include significant funding for the CHIPS Act. And while I think there are still details to be worked out of exactly how that funding should look, time is in short supply to address our future domestic chip needs. We need to act now, because I could tell you that our competitors aren't waiting. No matter what the final vehicle is for funding the CHIPS Act, I look forward to working with my colleagues to get it done as soon as possible. Thank you, Chairwoman Johnson, and I yield back the balance of my time.
Thank you very much. If there are members who wish to submit additional opening statements, your statements will be added to the record at this point. At this time, I'd like to introduce our witnesses. Our first witness will be introduced by Ms. Bonamici.
Thank you so much, Chairwoman Johnson. It is my pleasure to introduce Dr. Ann B. Kelleher, Executive Vice President and General Manager of Technology Development at Intel Corporation, which has several hubs or campuses in the district I represent and employs more than 20,000 Oregonians. Dr. Kelleher is responsible for the research, development, and deployment of next-generation silicon logic, packaging, and test technologies that power the future of Intel's innovation. Previously, Dr. Kelleher was the General Manager of Manufacturing and Operations, where she oversaw Intel's worldwide manufacturing operations, as well as corporate quality assurance and corporate services. Dr. Kelleher joined Intel in 1996 as a process engineer and has tremendous expertise to offer as a witness in this hearing. I want to thank her for being here with us this morning, and I look forward to her testimony. Thank you, Madam Chair, and I yield back.
Thank you very much. Our next witness is Mr. Manish Bhatia. He is the Executive Vice President of Global Operations at Micron Technology. In this role, he is responsible for driving the vision and direction for Micron's end-to-end operations. Prior to joining Micron in 2017, he served as Executive Vice President of Silicon Operations at Western Digital Corporation. He also served as Executive Vice President of Worldwide Operations at SunDisk Corporation when it was acquired by Western Digital. A third witness is Dr. Michael Witherell. He is director of Lawrence Berkeley National Laboratory, a position he has held since January of 2016. Prior to his position at Berkeley, he served as the vice chancellor for research at the University of California, Santa Barbara from 2005 to 2016, and was the director of Fermi National Accelerator Laboratory from 1999 to 2005. He is a member of the National Academy of Sciences and a fellow of the American Physical Society and American Association for the Advancement of Science. Our final witness, somebody introduce me.
Dr. Baird.
Dr. Baird will introduce. Dr. Baird, you recognize.
Thank you, Madam Chair. And it's indeed my pleasure to introduce to you an individual from Indiana's 4th Congressional District and Purdue University. Dr. Mung Chiang currently serves as the Executive Vice President of Purdue University for Strategic Initiatives, the John H. Edwardson Dean of College of Engineering, and the Roscoe H. George Distinguished Professor in the Elmore Family School of Electrical and Computer Engineering. Dr. Chiang's research on communication networks received the 2013 Alan T. Waterman Award, the highest honor to scientists and engineers under the age of 40 in the United States. And he has been the recipient of several other awards and distinctions. Most recently, Dr. Chiang founded the Center for Tech Diplomacy at Purdue, which intends to bring engineering expertise to policymakers in a way that demonstrates the inextricable links between technology advancements, and national interests. So, Dr. Chiang, we are very happy to have you here with us today, and we really look forward to your testimony. Thank you. I yield back.
Thank you very much. As our witnesses should know, you will each have 5 minutes for your spoken testimony. Your written testimony will be included in the record for the hearing. When you have completed your spoken testimony, we will begin with questions. Each member will have 5 minutes to question the panel. We now will start with Dr. Kelleher.
Chairwoman Johnson, Ranking Member Lucas, and members of the committee, thank you for inviting me to testify today. I lead technology development in Intel, where we research and develop process and packaging technologies for Intel's products. We also ramp this technology into high-volume manufacturing. Over the past 10 years, Intel has invested more than $75 billion in process and packaging R&D and US manufacturing capital. Over the next 10 years, Intel anticipates spending approximately $150 billion. This will cover our recently announced expansions in Arizona, New Mexico, and the US Greenfield site, as well as our future technology R&D. Intel's investments demonstrate our enduring commitment to the United States technology leadership, where we conduct all of our process technology R&D and the majority of our manufacturing. Semiconductors are fundamental to US technology leadership, our economy, and our national security, and we're the 4th largest US export sector in 2020. Recent supply chain disruptions due to COVID-19 and widespread chip shortages illustrate the risk to our economy and the danger of losing our ability to make leading-edge chips in the United States. America has lost significant share of semiconductor production to Asia over the last 30 years. For decades, countries in Asia have provided substantial incentives, driving a 30% cost disadvantage for chip making in the US, and a corresponding decrease in the US global share of manufacturing, and that dropped from 37% to 12%. At the same time, designing and manufacturing leading-edge chips has also become increasingly more expensive. A recent paper from Boston Consulting Group highlighted the fact that investments required to develop the next advance in chip making has grown 40-fold over the last 20 years. Due to this dramatic increase, Fewer manufacturers globally are able to make the investment required to develop leading-edge semiconductor technologies. In 2000, more than 25 companies built leading-edge chips, but today only 3 leading-edge manufacturers of logic technology remain, and Intel is the only one left in the United States. 3 essential ingredients are necessary for a strong US semiconductor industry. Manufacturing process technology, including IP and know-how based in the United States. US fab capacity to support the growing demand in the US and worldwide, and advanced packaging capability and capacity. But these essential elements are being challenged by the 30% cost disadvantage and the lack of public funding for R&D. 40 years ago, federal investment in semiconductor R&D was more than double that of private investment. But today, US private investment is nearly 20 times that of public funding. Federal investments is urgently needed to level the playing field and reverse the erosion of US semiconductor industry. Congress must enact funding of the new semiconductor manufacturing and R&D programs created in the CHIPS for America Act as soon as possible. The CHIPS Act has the right framework to create a strong US semiconductor industry, and I'm confident that if funded in a robust and sustained manner, these programs will significantly contribute to American technology leadership. Once funded, the federal government will need to effectively implement the CHIPS Act most significant new R&D program, the National Semiconductor Technology Center, or NSTC, and the National Advanced Packaging Manufacturing Program. For the NSTC, Intel recommends prioritizing R&D on future breakthrough challenges that align with industry goals, leveraging existing industry infrastructure to save time and reduce cost. NSTC should be led by a neutral nonprofit that can reconcile conflicting needs in the industry. For the packaging program, Intel recommends establishing a physical location for the participants to work together to develop leading-edge, cost-effective packaging technologies in the United States. The program should encompass packaging integration efforts across the semiconductor ecosystem. The committee has an important oversight role regarding the CHIPS Act program, and Intel looks forward to working with you to provide our perspective on how to effectively implement these programs. Thank you for holding this stakeholder hearing, and I look forward to answering your questions.
Thank you very much. Mr. Bhatia.
Chairwoman Johnson, Ranking Member Lucas, and members of the committee, I'm honored to appear before you today to discuss the status of U.S. leadership in advanced semiconductor development and manufacturing, particularly as it relates to memory and storage technology. Chairwoman Johnson, please allow me to congratulate you on your upcoming retirement and thank you for your decades of distinguished service. My thanks to you and to the members of this committee who are spearheading the bipartisan effort to ensure long-term U.S. leadership of critical semiconductor research and development and manufacturing capability. With your permission, I will submit my full statement for the record. I testify today as Executive Vice President of Global Operations at Micron, the world's memory and storage technology leader. Micron is the only company developing leading-edge memory and storage technology in the United States, and the only firm manufacturing DRAM, dynamic random access memory, or NAND flash memory in the United States. Headquartered in Boise, Idaho, Micron is the world's 4th largest semiconductor integrated device manufacturer and the 2nd largest in the United States. We have 43,000 team members worldwide and nearly 10,000 of them located in facilities across the United States, including in our Manassas, Virginia facility, where we manufacture memory and storage solutions that are critical to driving growth in the expanding automotive, industrial, and networking markets. Today, I hope to leave you with 2 key takeaways. First, memory and storage technologies are essential to a digital and data-intensive future for the United States. And second, long-term substantial investment in leading-edge semiconductor research and development and manufacturing is vital for the United States to maintain technology leadership across diverse end applications from the cloud to the edge and everywhere in between. Memory and storage are foundational for every computing paradigm, creating a meaningful domestic manufacturing base through funding of incentive programs such as those included in the CHIPS for America Act and implementation of a refundable investment tax credit will enable a domestic supply of these essential devices. Micron designs, develops, and manufactures industry-leading semiconductor memory and storage products, the most common of which are DRAM, which provides rapid access to data for processing, and NAND flash, which provides long-term data storage. These products are critical to all sectors of the US economy and to national security. By providing foundational capability for artificial intelligence and 5G across the data center, the intelligent edge, and consumer devices, Micron's products unlock innovation across industries, including healthcare, automotive, and communications. Computing workloads of the future are increasingly data intensive, requiring highly reliable, high-performing, and power-efficient advanced memory and storage solutions to optimize results. Memory and storage have grown from 10% of the global semiconductor industry revenue in the year 2000 to about 30% of the semiconductor industry revenue today. We expect this trend to continue. For example, 5G phones have 50% more memory and twice the storage content as compared to 4G phones. Autonomous vehicles of the future will require as much DRAM and NAND storage as today's servers, as cars become data centers on wheels. Conversely, domestic semiconductor manufacturing has experienced a steady decline. For example, in 1990, the United States had 37% of global chip manufacturing capacity and now accounts for only 12%, and only 2% of global memory production. Micron has developed and is producing the world's most advanced DRAM technology, 1 alpha nanometer, as well as the most advanced NAND technology, 176 layer. Our technology leadership is based on an unwavering commitment to innovation in both research and development with our aggressive technology roadmap, and manufacturing, where we deliver these industry-leading technologies at scale. We believe Congress should focus on 3 key areas when considering the conditions under which long-term U.S. leadership of these critical semiconductor technologies can flourish: research and development, manufacturing, and workforce development. We stand ready to work with this committee and others in Congress and the executive branch to ensure the United States achieves and maintains the world's leading digital and data-intensive economy in the decades ahead. Thank you again, Chairwoman and members of the committee, for the opportunity to participate today, and I look forward to your questions.
Thank you very much. Dr. Michael Witherell.
Hello, Chairwoman Johnson, Ranking Member Lucas, and distinguished members of the committee. Thank you for holding this important hearing to focus light on this critical national challenge. I appreciate the opportunity to provide testimony. I've been Berkeley Labs Director since 2016, was previously Director of Fermilab. For over a decade, I have become steadily more concerned about the increasing threat to the nation's leadership in semiconductors. Strengthening the nation's entire microelectronics system, breakthrough research, technology development, and domestic manufacturing at scale is imperative for the nation. I do not need to convince people at this hearing how central the advanced semiconductor industry is to much of our economy. Although industry has the central role, it is increasingly clear that our nation's ability to lead the world in the development and deployment of advanced semiconductors will require a strong commitment across the entire federal government. It really is the time for an all-hands-on-deck approach that requires new investments across the innovation ecosystem, industry, academia, and the Department of Energy national laboratories. Why should DOE have a major role in the National Microelectronics Initiative? First of all, as you are aware, the Department of Energy is the largest supporter in the U.S. of the physical sciences and is the national leader for research in the fields that underpin microelectronics, physics, chemistry, material science, and computer science. This leadership has led to over 100 Nobel Prizes awarded to DOE-affiliated researchers, many for breakthroughs with profound impact on society. Second, sustained federal investment at the national labs has developed highly managed teams of the world's best scientists and built world-class large-scale research facilities. These represent a unique combination of assets that the labs can bring to the full R&D ecosystem that is needed to help meet the current challenge.
These lab assets can be deployed immediately with appropriate support. Third, the continuation of microelectronics evolution along the path of business as usual would require an unsustainable amount of the world's energy budget. We cannot meet the national energy goals without addressing the future of microelectronics. Conducting research to dramatically improve the energy efficiency of microelectronics is a science and technology challenge that falls squarely within the DOE's energy mission space. I want to emphasize that the DOE national labs already have a long history of working together with the semiconductor industry on pre-competitive research that has helped push the boundaries of what silicon chips can do. Several facilities have been developed at DOE labs to support the semiconductor industry's existing capability to fabricate devices with feature sizes of several nanometers. Semiconductor companies working collaboratively here at Berkeley Lab have made over $160 million in investments at a specialized facility at our advanced light source to support the industry's campaign to shrink the feature size on chips to widths and depths of a few dozen atoms using extreme ultraviolet EUV lithography. This industry investment is even larger than stated in my written testimony, since we just did a full search of the records over the history of that center. The DOE Office of Science invests more than this for the underlying operation of the X-ray light source facility that hosts this center. The investment from industry has been for the specialized instrumentation, research, and components that enabled the center to leverage the federal investment. For another example among many, the Center for Nanoscale Materials at Argonne National Laboratories offers extreme scale device processing, as do all 5 of the nanoscale science research centers at DOE labs. And the MESA Fab complex at Sandia National Laboratories develops and maintains core semiconductor capabilities needed to support the DOE's nuclear security mission. In addition, the world-leading advanced X-ray sources at DOE labs enable researchers to characterize with high precision the new materials and novel devices needed for ultra-efficient computing. And completing the cycle of technology development requires the computer modeling capabilities that the DOE's high-performance computing facilities provide, with specialized software and applications developed for these platforms. I would also like to emphasize the importance of developing the highly trained workforce needed to keep us as the leader. So in conclusion, our nation's global reputation for innovative technology is due in large part to the health of the entire ecosystem for research, development, and deployment, with a focus on establishing a domestic manufacturing base. This will require a full science-to-systems approach that leverages the national labs to provide the fullest possible support to the industry. Thank you for allowing me this opportunity to speak to you today.
Thank you very much. Our final witness is Dr. Mung Chiang.
Chairwoman Johnson, Ranking Member Lucas, and distinguished members of the committee, thank you for the opportunity to testify today. My name is Mung Chiang, the Executive Vice President for Strategic Initiatives at Purdue University, and the John A. Everson Dean of the College of Engineering. And this year, Purdue's College of Engineering became the largest engineering school to be ranked among top 5 in the United States, with over 15,000 students enrolled. Purdue also has over 100 faculty members working in microelectronics and related fields. And our digital economy is built on silicon. It helps to visualize the supply chain in 5 steps. First, there's the raw materials and gases needed to make chips. Then there are hardware tools that go into chip factories. Third is the design of chips and the software tools used in such design. And American companies continue to lead the world in chip design. Then is manufacturing, taking all of the above into a factory. The physical making of chip goes through many processes. Some factories focus on logic chips, while others on memory and storage chips. And finally, assembly, test, and packaging. Once chips are made, they need to be packaged and integrated into the microelectronic products, and eventually find their way into phones, cars, fighter jets, and more. Much of the discussion these days zooms in on the manufacturing step, and there are 2 different types of business models. One is to make chips designed by the same company, and the other is to make chips designed by other companies, the foundry model. With increasing specialization in the semiconductors industry over the past 3 decades, many companies have chosen to become fabless and rely on the foundry. This in turn enhances the foundry's benefits of scale and sharpens its ability to deliver cutting-edge manufacturing under a service mindset and trust with the foundry customers. For the semiconductor industry in the US, across the whole supply chain, we are in the critical years now. Universities have 3 unique roles to play in this silicon moment. One is to help create synergies with companies, large and small, to bridge fundamental research advances with commercially deployable technologies. An innovation ecosystem works best when we create synergy across major companies in manufacturing and in design, small to medium disruptors with their investors, and researchers and teachers at universities. A second role is educating and retraining large numbers of engineers, technicians, and operators. Ideally, university can create knowledge and jobs together, generating both new positions and the talent needed to fill the positions.
It's going the wrong way.
And third, universities, especially land-grant institutions such as Purdue, have an obligation to serve as an economic driver for the state, and there's no greater opportunity today than in microelectronics. And Purdue is proud to be a partner with the state of Indiana, developing strategies and providing a talent pool. For the future of chips, the ultimate supply chain is that of human talent. In just the next 5 years, at least 42,000 semiconductor engineers need to be trained and ready nationwide, and the number will continue to climb well into the next decade. There is a growing gap between the supply and demand for microelectronic and semiconductor engineers across the spectrum, from associate and bachelor degrees to masters and PhDs. And some specific steps need to be made, include revising, reinvigorating, and expanding the microelectronics curricula with expanded use of hands-on training, online learning, partnership with community colleges, and engagement with industry. And also to scale up such educational programs and substantially increase the number of scholarships for undergrads and fellowships for graduate students in the United States. And third, to fund research and development programs that push the boundaries of science and engineering and facilitate the translation of new discoveries into applications. And action is indeed needed now. Passing the USICA and funding the CHIPS Act this month will be a crucial and timely win for the national security, economic security, and job security in our country. Thank you.
Thank you very much. At this point, we will begin our first round of questions. The chair recognizes herself for 5 minutes. I'd like each witness to comment. As you've all testified, the United States faces several challenges to maintaining U.S. leadership in microelectronics. They include a lack of domestic manufacturing and packaging capacity, a limited technical workforce, technology transfer challenges, and multiple scientific challenges. Given that the availability of resources may never be enough to fully address all of the many challenges, how should the federal government set funding and policy priorities? In particular, since this is a science committee, how should we prioritize policies and funding to maintain leadership in semiconductor innovation?
I will start. So my recommendation is that this committee needs to look at some of the key breakthroughs that are needed for the long haul to maintain the overall research and development and the future of the industry. the funding which comes with the CHIPS Act, once the funding is received and arrives, it doesn't have an immediate impact as far as the longer haul. So I believe that we as a semiconductor industry need to identify the top key areas in terms of that we need to continue to develop from material science, from lithography, from all the aspects that continues to keep moving our research in the 10 to 15 years out, so that we can set ourselves up for technology leadership for the long haul.
Sure. Chairwoman Johnson, I can go next. I believe that the prioritization should be towards leading edge technologies, whether in research and development or in manufacturing. Chairwoman Johnson, as you noted in your introductory remarks, and as Ranking Member Lucas noted in his, from the dawn of the semiconductor era with the invention of the integrated chip to today, the thing that makes the semiconductor industry unique is the rate of change of technology and that cadence that continues to move. Every 18 to 24 months, new technologies are introduced that are higher performance, higher density, and lower power. And so the biggest challenge that we face as an industry is continuing to maintain that the leadership in advanced leading edge capability for process technology, for device capability, and in manufacturing. So our recommendation is that the funding, both for research and development, as well as for manufacturing, focus on leading edge technologies, because these are the areas that are going to ensure American leadership in microelectronics far into the future. And both the CHIPS Act, as well as refundable tax incentives that are being proposed, are both necessary measures to be able to ensure that this can happen.
So I can go next, and I would say for the federal investment in R&D, I think keeping that focused on the laboratories that are best connected with the industry. This has to be laser focused on working through the problems that industry is facing on developing the new technologies. And so there are longstanding partnerships, public-private partnerships on working through this, as we have at several of the laboratories and at some academic laboratories as well, to make sure that we're solving the problems that industry needs to work our way through this. The other thing I would say is that we need a bigger workforce, a more capable workforce working in these hardware technologies than we have today. You heard about it from our dean. Supporting the academic environment so we can grow this workforce is essential too.
First, a mic check, see if you can hear me. Great, thank you. I was worried that I've lost my engineer's ability to adjust the volume on my computer. So great to know that you can hear me now. Well, I want to just echo what my fellow panelists have already mentioned. There is the need to fund and prioritize ideas for the future. And then there is the need to fund people that's needed today. For the ideas for the future, as we mentioned, activities in R&D in areas such as advanced packaging, heterogeneous integration, new material, and going from 2-dimension to 3-dimension are all essential to the continued R&D vibrancy of semiconductors industry in the United States. As to the people that we need today, it would take a grand strategy across government, industry, educational institutions, K-12, as well as government national labs to work together. In particular, to deploy more online learning for upskilling and retraining of existing workforce, to substantially increase the number of K-12 student pipeline into engineering programs in the country, and to increase the use of hands-on learning, industry internship opportunities to make sure that they're ready for the market. And all of these can be further supplemented by increasing the number of scholarships for undergraduates and fellowships for PhD students in the country. And finally, we do need, indeed, diversity in the range of talents, including those who are in community colleges, and also inclusivity in the geographic balance. There are many talents throughout the country, and they can all be part of the solution to the workforce shortage problem. Over.
Thank you very much. The chair now recognizes Mr. Lucas for 5 minutes.
Thank you, Madam Chair. And before I begin my question time, could I take a moment to introduce the newest member of the Science Committee?
Yes, you may.
Thank you, Chairwoman Johnson. And I'd like to welcome Mike Carey as the newest member of our committee. He joins us from Ohio's 15th District. He brings decades of experience in the energy industry. And I know he's eager to get to work helping us strengthen and modernize the American energy production with an all-above approach to new energy technologies. I know he'll be a valuable member of the committee, and he's learning the joys of our Wi-Fi and logging in on a web meeting right now. So it's a character-building experience. Thank you for joining us, Mike, and thank you, Madam Chair, for that.
Well, thank you, just a minute. Let me welcome you and say that you're joining the greatest committee on the Hill. Thank you.
That's what I've heard.
And the chairwoman is absolutely correct. That said, and the remaining year of the chair's time, we're going to work her really hard as we accomplish great things on this committee. Now, that said, Dr. Kelleher and Mr. Bhatia, as I mentioned in my opening statement, I'm interested in hearing from both of you about the lessons learned, good and bad, from the federal government's previous efforts to bolster U.S. competitiveness in microelectronics and its support of semitech. I would also be interested in your insights on how IMEC is successful and where it may fall short. In other words, what characteristics of these programs should we consider adopting for the NSTC and other CHIPS programs, and what should we avoid? Let's talk about the lessons we've learned.
And maybe I will start with, because I'll start with IMEC, because I myself worked at IMEC earlier in my career. So I have first-hand knowledge. I have a lot of respect for IMEC and the work that it has done, and its ability to make itself self-sustaining over the years, and the work that it's done enabling for the basically research, not just for Europe, but for worldwide. I think one of the key learnings from IMEC is IMEC works in the research in its pre-competitive space. And that pre-competitive space enables it to do the early research that feeds into the overall industry as a whole. It's in parallel to some of the universities, but it also feeds into the overall, basically the ecosystem as a whole. That pre-competitive research goes to the semiconductor fabs, and it goes to work with the equipment vendors and the material vendors. So basically it's quite strong. I think one of the key things is we have a lot of basically discussion on how does one get access to prototyping, etc. IMEC is not a model that's set up for prototyping. IMEC is very much in the pre-competitive space. So I think as we go forward in this, one of the lessons learned is how do we take the equivalent of working with the research institutes and working with for the pre-competitive space and funding that, as well as taking it further down the supply chain in terms of how we set up so that we enable prototyping and eventually enable turning that product into basically leading edge products here within the United States. I think I will let, given I'm consuming time, I let Manish take the semitech.
Please.
Sure. Thank you, Dr. Kelleher and Ranking Member Lucas. As you mentioned, when Semitech was founded almost 40 years ago, there were more than 20 American companies who were doing leading edge process technology development as well as manufacturing. And today, really the two companies on the panel are the ones who are doing that left in the United States. So the Semitech model, while it served its purpose for a prior era, a replication of that would not necessarily provide the same benefit that it did now, because really Intel and Micron are the two companies that are doing leading edge process development research and leading edge manufacturing among the U.S. companies. With regard to the, what the focus for this committee can be to help fill a gap that exists, we agree with Dr. Kelleher's comment that while focus on university research as well as the national laboratory network have been excellent programs and continue to be vital areas for long-term foundational research. And those, do need to have funding increase to be able to maintain our status as leadership around the world. This transition from the labs of those national labs or of those universities to the fabs that we operate is the area that we can help to bridge with the National Semiconductor Technology Center's approach and rapid prototyping of new technologies to accelerate the time from their demonstrated feasibility in laboratories, in university or national lab environments until they can be commercialized and ramped at scale in high volume manufacturing. This is the area that we see as a primary focus for the funding for the NSTC.
Dr. Chiang, I want to thank you for your comments on the need to build a workforce to meet the demand that will come with a growing domestic semiconductor industry. And I'm especially appreciated your comments on the need to train technicians and production workers. Like Indiana, which has Ivy Tech, Oklahoma has a remarkable program with Career Tech. Tech schools and training offer a tremendous opportunity to train, reskill, upskill America's workforce. Can you please elaborate on how Purdue is working with Ivy Tech to develop workforce programs focused on skills needed by the semiconductor industry and how that potentially could serve as a model?
Thank you, Ranking Member Lucas. I would be, first of all, again, mic check if I'm still all right with the volume. All right, fantastic.
I can hear you.
All right, thank you. That indeed, it takes a whole partnership. No university by itself can fulfill the whole spectrum of needs. It takes partnership, and I'll highlight 3 partnerships. One is, as you mentioned, Purdue University has been partnering with Ivy Tech, which is our statewide community college system with over 70,000 community college students. And we also have started deploying a new set of degrees and credentials, including a dedicated degree at the master level for semiconductor supply chain, from the material and the gases needed to the hardware tools needed to the manufacturing and the design, and eventually to test assembly and packaging. And third is the use of online learning to share these new spectra of curricula with other learning institutions. And under President Mitch Daniels, Purdue University's leadership, Purdue Global and Purdue Online for the West Lafayette Main campus have rolled out a wide variety of online learning certificate and opportunities, so that even those who are in the workforce today wanting to upskill, or those who are remote learning and not able to attend the university within Indiana will be able to benefit from these results. And finally, I would just comment also how the industry and academia can work together, even in education space. It takes more than just recruiting, but also actively participating in the design of these curricula, in providing hands-on learning internship opportunities, in providing workforce training for their own employees through our online degrees. And these cut across the bachelor degree and associate degrees, as well as more advanced degrees, so that it's not just universities generating the supply of talent, but truly industry and universities working together to design the curricula and to educate these workforce together. Over.
Thank you, Doctor, and thank you, Chair, for indulging me on the time. Yield back.
Ms. Bonamici is recognized.
Thank you so much, and thanks to the chair and ranking member and our witnesses. And before I turn to my questions, I just want to acknowledge the chairwoman on her recent announcement. Chairwoman Johnson, it's been and continues to be an honor serving with you and your leadership, and I'm looking forward to a very productive upcoming year before a more formal farewell. It's clear that we have a lot of work to do to expand and preserve the role of the United States as a global leader in semiconductors. It's also clear that we need to swiftly provide funding through the CHIPS Act, as both the chair and ranking member have mentioned, to help reinvigorate our nation's semiconductor industry. And we've all heard about the semiconductor shortages, primarily pandemic-induced, disrupting countless sectors across the global economy. And the district I represent, which is often referred to as the Silicon Forest, is particularly vulnerable to these supply challenges. Thousands of my constituents, more than 40,000 Oregonians, currently work in the semiconductor industry. So there's tremendous potential for that number to grow. And I want to note that every witness here today raised workforce issues. Workforce readiness is a major limitation to expanding U.S. Semiconductor leadership. And as a member of the Education Labor Committee, this is something that I care about deeply. So Dr. Kelleher, nice to see you again. Thank you for joining us. What on-the-job training program does Intel offer to prepare its own workforce? And as an industry leader in semiconductor employment, we're really interested in your opinion about what steps Congress could take to boost the industry's workforce pipeline.
Thank you very much for the question. And it's absolutely my honor to talk about workforce development because it's very near and dear to my heart. And when I was leading the manufacturing organization, it was also very important to me. The span of workforce development covers it covers an entire span. Within our factories, it covers the span from our skilled technicians to operators, right up to the most advanced researchers we can hire. Equally well, we're building factories, and the entire trade availability and the entire trade skill is a declining skill, and there's a shortage within the trade community. So I would say this entire semiconductor industry, the skills that needs to be grown, it goes anywhere from in the construction industry to support the building of our factories, right up to the most advanced researcher. Within Intel ourselves, we have quite a lot of training programs. We have in-house training programs where we, as we hire our technicians, they're in-house training on the equipment and associated training to get them up to a certified level. We hire quite a lot from the military, and of employees we hire from the military come to us with a really good standard, and that makes that training basically easier. And we also work with the universities and the colleges. And over the years, we have done many programs with the colleges to actually get the programs and the specifics that we need in, and some to train for folks we've already hired, or B, to set up classes and to set up training programs so that we can hire from those. So across the board, I believe there needs to be a generic, I would say, focus and look to go anywhere from our supply into construction to enable us as an overall industry to build our factories. And also with the universities and with the and with the, I will say, the less skilled aspect of it, but there is no low-paying job within the semiconductor industry. They're all skilled jobs. So
understood. Thank you. And I'm sorry, I don't mean to cut you off. I just want to squeeze in a question real quickly for Dr. Witherell. Thank you for that comprehensive answer, which was really helpful. Dr. Witherell, according to your testimony, the microelectronics energy consumption is projected to increase from 5% of the world's energy use today to 25% by 2030, which of course is a significant increase. And you recognize that research to address this challenge falls squarely within DOE's mission. So what efforts are underway to research how to reduce energy intensity across the semiconductor supply chain? And do you have any examples?
Well, we are working on new materials and new devices to break through that energy barrier in semiconductors, and that's something that's actually squarely in the energy space of the DOE laboratories, but also it's in the science technology space, and so that's why we're putting that in the lead. And the important thing is actually having, for this pre-proprietary research to be doing in the labs, but closely tied to what the industry is ready to do. And that's why these continuing public-private partnerships are important. I also want to, as another example of that, Princeton Plasma Physics Lab is working on plasma processing with industry and academia for processing, which is another important thing I didn't have the time to mention in my testimony. Taking advantage of these existing partnerships is the way to get faster movement from the DOE laboratory into industry, which is what I think we're hearing about.
Terrific. Thank you so much. I'm out of time and yield back. Thank you, Madam Chair.
Mr. Babin is recognized.
Thank you, Madam Chairwoman Johnson and Ranking Member Lucas, and thank you to the witnesses as well for being here with us today. Demand for semiconductors is at an all-time high, which is a trend unlikely to ease off for the foreseeable future in our country's evolving reliance on digital infrastructure. From smartphones to our defense technologies, semiconductors continue to play a critical role in our country, and investing in this industry should be a high priority for us. Texas alone has seen several investments made in the semiconductor industry this year, with Samsung announcing just last month a $17 billion investment for a new facility in Taylor, Texas. Not in my district, but I'm proud to have them in Texas. One of the biggest investments we've seen in many a long year. In fact, maybe the largest. It's important that we pursue American competitiveness in this industry. We recognize the role of partnering with companies abroad, which are important players in our supply chain. So, Dr. Chiang, in your written testimony, when evaluating the semiconductor supply chain, you mentioned the 3 Ps: protect, promote, and partner. Recognizing the importance of focusing on these key aspects of the supply chain, would you please elaborate on how the United States can best leverage our valuable taxpayer dollars with our allies to ensure the U.S. remains a leader in the global market? And how do we continue to encourage investments in the future in domestic growth and in American jobs?
Thank you very much, Congressman,
Yes,
for the question. For the 3 Ps, usually people are referring to public-private partnership, which is certainly important. And I was referring to the 3 dimensions of protect, promote, and partnership. And on the partnership front, we have to recognize that it helps for the United States to onshore like-minded nations' private sector success. For example, Congressman, you just highlighted Samsung from South Korea's investment into the Austin neighborhood in Texas, and congratulations. And of course, we saw in May 2020, TSMC, a Taiwan semiconductor manufacturing company, one of the largest, the most leading edge manufacturer of semiconductor chips, coming to the United States, to Arizona. And we have other like-minded nations partners in the design space, such as MediaTek, also from Taiwan. And we just mentioned some of the partnership with European countries as well. I think it is of utmost importance to encourage these partners to come to the U.S. shore, to create jobs in America, to produce results and intellectual property in the United States, and also to work with American companies, both to create jobs for our students and to help us to train such students together. And here at Purdue, we're proud to work both with companies such as Intel and Skywater and other American headquartered companies, but also with companies such as TSMC and MediaTek.
Right. Thank you so very much. And Dr. Chiang, you also mentioned that the U.S. is the largest end user of semiconductors in the global market, but yet the U.S. share of global semiconductor fabrication is only 12%, a very low number. And Dr. Kelleher, you highlight the same shocking percentages in your written testimony, and going on to highlight the danger of losing our ability to make advanced chips in the United States. So both of you, if you please, would elaborate on what you see as the biggest threat to our semiconductor supply chains.
Our biggest threat in terms of our semiconductor supply chain is our ability to continue to, I would say, invest and grow and keep that advanced leading edge R&D and IP growing within the United States. We're at a fundamental disadvantage compared to some of the Asian countries when it comes to basically developing and manufacturing our chips. So if we lose our ability to actually continue to maintain that leading edge manufacturing, it means that as a supply chain, we're completely reliant on the rest of the world. And I don't believe that's a good place for the United States to be.
No, ma'am. And Dr. Chiang?
Thank you, Congressman. I agree with Dr. Kelleher's assessment that indeed we need to make sure that the entire supply chain is secure. That includes gas and materials needed, including rare earth minerals. That includes the tooling companies. We have companies such as Applied Material here in the US and Tokyo Electron, both of which work with Purdue and the state of Indiana. And that includes the manufacturing companies as well as the chip design companies. And even more depressing numbers can be found when it comes to the final step, advanced packaging. And we need to onshore or reshore a lot more on the packaging front as well. Here in the state of Indiana, Governor Eric Holcomb and the whole team here have been trying to increase the presence of packaging as well as manufacturing facilities. Some of that is upgrading existing ones in universities, such as Purdue's Berkeley Nanotechnology Center and the NanoHub virtual learning platform, and others are new ones. And I would wrap up this brief comment and answer by highlighting the optimism that I have, that as somebody once said, never short on America and Americans. The ingenuity and the creativity of our universities and companies and government lab is truly second to none. And as long as we continue to look forward to the most innovative R&D ideas and run faster than we have ever run before, then there is no limit as to what American ingenuity can do. Over.
Great. Thank you both so very much. And I yield back, Madam Chair.
Ms. Stevens is recognized.
Ms. Kelleher, what can you tell me about the origin of semiconductors, given the company you work for and who your founder was, Mr. Gordon Moore?
Well, let me start with just Gordon Moore, Robert Noyes, and Andy Grove are the three founders of Intel. Intel was basically incorporated as in 1967-68, so we're well over 50 years old as a company. So semiconductors in basically are the essence, and I speak very much for transistors right now, not memory. But the essence of semiconductors is basically a switch. The essence of this switch is you can switch it on or off from a silicon perspective. And the combination of all of these transistors put together enable circuits to get designed, which ultimately are able to do computation analysis and very complex analysis. And as we progress over time, we're moving into the artificial intelligence space where there's overall trading and workload. So over the years with the industry, when it started, it was basically we were working with very large dimensions. And what today, when we look back, were not complex transistors, nor were they really large or complex designs. Probably were viewed like that at the time, but today when we look back, as we progress over time, the nature of the semiconductor to make, as we continue to advance on the Moore's law scaling, so that approximately every 2 years we're doubling the amount of transistors that you can fit in a chip.
Right. Well, and Dr. Witherell would note that, and just pardon me on this front, because he would note that Mr. Moore, and I know he wasn't the exclusive founder of Intel, was at the university level and then broke off, was working for a semiconductor company and then joined with his colleagues to form Intel. And it's quite inspiring. Intel and Micron, Manish, you also represent a very large employer, and we're very inspired by your companies, and we're inspired by the employability, the R&D. The question is, and Manish touches on this in his testimony, is that at one point, right, we were innovating, we were inventing, we were creating these incredible enterprises of scale, producing in this country 40% of chips. And I come from Michigan, and we've got an auto sector that relies on this, and we're at 12% today. And Manish talks about this, that, it costs 35 to 45% more to have chip manufacturing in the United States. Why? Why? Can you answer? How do we make this more competitive for you? How do we compel you? Because it's not just a feel good, right? It's not a cute thing to say, oh, we like manufacturing in this country. This is our bottom line. This is our economic competitiveness. We have an XM bank in this country that gives us a platform to trade globally, to export. Many years ago, some of my colleagues might remember this who were here. This was on the other side of the aisle. They were going to get rid of the XM bank. They were going to get rid of the XM bank. And industry said, oh my gosh, we won't be able to compete. Now here we are, the tide has rolled out. Billions and billions of loss of profit, losses of jobs. How do we bring it back? What do we need to do to bring it back here? Get people back to work and increase our production capabilities in the United States for semiconductors.
So, Representative,
Go ahead.
I'm sorry, was that for me? Was that question for me?
You can be for you. You touched it. I mean, everyone had a brilliant testimony. I mean, really, these testimonies were incredible.
So, Representative Stevens, thank you for that. I'll touch on that, and then I'll let other panelists. To answer your question, the 35 to 45% cost gap to build and operate large-scale semiconductor manufacturing facilities between lower cost regions in Asia and the United States is really comprised of three elements. The first is labor costs, both for operating the fabs, but also for construction of these fabs. These fabrication facilities, each one will cost multiple billions of dollars just to build the clean room facilities before we even start to equip it. And then with equipment, they become above more than $15 billion for each individual site. So the labor cost for both the construction and the operation is the first element. The second element is really the scale of the facilities. Over the last 20 years, Asian countries have had focused policies to be able to grow the ecosystem, to grow semiconductor manufacturing, particularly for memory, into larger and larger scale. So when we're starting from small scale, or in some cases no scale, the economies of scale that are enjoyed in Asian countries because of the investment over the last 20 years drive a substantial cost gap as well. And then the third piece is the government incentives that are there. And we believe that the CHIPS Act and a refundable investment tax credit that has been introduced and proposed, these are the right first steps to be able to try to reverse this trend and make it more cost competitive for U.S. integrated device manufacturers to build large-scale semiconductor manufacturing facilities. And the other point that you mentioned about jobs is very important. Each of these facilities require and create thousands of high-paying, high-value jobs, whether you're talking about scientists in the labs or engineers operating the fabs or skilled trades operating this high-precision equipment and these very, very exacting and demanding clean room environments and maintaining the facilities. These are high-paying jobs that are that create long careers and improve the quality of lives for every one of the communities where we operate. So investing in the future in semiconductor manufacturing has benefits both economically as well as in the local communities and their quality of life.
Well, I'm egregiously over time, but Dr. Witherell, we're going to do, and Dr. Chiang, we'll do a QFR. We'll do a question for the record because the public-private partnership component here is also incredibly imperative. Thank you. I yield back.
Mr. Gonzalez is recognized.
Thank you, Mr. Chair, and Ranking Member Lucas for holding this hearing, and to our witnesses for joining us this morning. I want to take a brief moment to thank Chairwoman Johnson for her leadership and commitment to our committee over these many years. I've been a member for 3 years now. I've announced my retirement for a lot of reasons, one of which is this place just operates like junior high is probably generous in many respects. With the exception of this committee, and this committee operates, and this place operates in large measure on the cadence of the leadership. As leadership goes, so does Congress. And my belief is that this committee is so effective because we have such effective leadership. And that starts with Chairwoman Johnson and Ranking Member Lucas. And so I am enormously grateful for her service. I'm sad to see her go, but it's much earned. And she has certainly served our country and her district incredibly well. We will miss her, but I'm cautiously optimistic. I'm very optimistic that whoever takes over in the coming years will carry on the tradition, because we've been effective and we need to be effective. As nothing more important from a economic development standpoint, in my opinion, than reshoring our semiconductor manufacturing. I'll start with Mr. Manish Bhatia. You were just talking about these facilities, and I want you to kind of go a little bit deeper and give us a sense of the scale. When a new fab is produced, when we come and say, okay, we're going to make major investments in a community and increase our manufacturing, what does that look like from an economic development standpoint? Think of I'm from Ohio, think of a town in Ohio and what those sorts of things can mean, what those sorts of investments can mean for individual communities.
Sure. Thank you, Representative Gonzalez, and thank you also for your service. As I was starting to say before, to operate a large-scale semiconductor manufacturing facility requires thousands of employees of the manufacturer, whether they're engineers who are developing process or maintaining the process, managing the yields and the quality levels and the productivity through the fab. But we'll also have almost an equal number of thousands of jobs of indirect employees who are on the site every day, whether it's to continue with construction or installation of this high precision equipment, maintenance of this high precision equipment, installation and maintenance of the specialized chemicals and gases that we need to operate the clean room or to manage the processes on the floor, or to just operate the overall facility. So we're really talking about thousands of direct jobs that are employees of the manufacturer, and then thousands of employees who are on site that are from the contractors or the equipment companies or the chemical and materials companies. And then you have the support in the community for those large-scale manufacturing operations. We believe that those thousands of jobs have a 3x multiplier in the community to be able to support these large-scale investments. As I mentioned, a single fab will cost more than a modern fab today will cost more than $15 billion in capital investment. And when we talk about memory fabs and minimum efficient scale, single site facilities are not minimum efficient scale today. We need multiple fab clusters that similar to those that have grown up in Asia to be able to be cost competitive. And so you're really talking about massive, long-term, decades-long investments that can prop up entire communities and can improve the quality of life, whether we're talking about high-paying jobs, but you're also talking about infrastructure in the community, healthcare in the community.
My time just for a second, because I only have a minute, but I appreciate the enthusiasm, and I would commit to everyone on all of our panelists. Ohio is ready. Ohio is ready, willing, and able to support semiconductor manufacturing right now. So we are open for business. Please come. We will provide the incentives. We will do all that we can, I can assure you. With my final point, you mentioned government incentives and refundable investment. We have to make it more cost competitive. At the end of the day, the companies answer to shareholders and have to be more cost competitive. I'm just going to make a brief comment and then yield back. My Democratic colleagues are considering massive spending and various forms of tax increase through Build Back Better. Whatever you do, please, please, please be very cognizant of the fact that if you raise corporate taxes or if you do something to make us less competitive economically, that's going to reverse many of the benefits from the CHIPS Act. So buyer beware on that stuff. With that, I yield back.
Mr. Bowman is recognized.
Thank you so much. And Madam Chairwoman, I want to echo the sentiments. Congratulations on your retirement. Thank you so much for showing us the way, or showing me the way as a freshman, in terms of how Congress is supposed to work. Thank you for your leadership on this committee. My question is for Dr. Kelleher. Thank you for your testimony. Intel is a large, very successful company that made $21 billion in profits last year and spent over $14 billion on stock buybacks. Intel's CEO recently acknowledged that stock buybacks have undermined the firm's competitiveness. I believe Intel has been talking about expanding domestic manufacturing capacity for some time now, and it strikes me that you already have the ability to do so. What material impact would Intel's portion of CHIPS Act incentives really have? You touched on this earlier, but I wanted to come back to it. Why is a subsidy like this going to make the difference in terms of delivering new leading edge capacity in the United States?
Well, first of all, I obviously very clearly said we have a long commitment to the United States, and in terms of our investment in R&D and manufacturing over our 50-year history. This fundamentally, in terms of the CHIPS Act, is about enabling us to maintain competitiveness here within the United States. We are continuing to invest in leading edge technology development and manufacturing for us to continue to compete effectively with the competition worldwide. The CHIPS Act is absolutely essential for us to enable to do that. So I think that is my simple answer to you, Representative Bowman.
Okay, thank you. I may come back to you if time allows. I had a question about creating pipelines for young people who want to go into careers in this sector. It was mentioned by a few of the witnesses. I want to focus on, someone mentioned K through 12. I want to focus on the high school setting. What should high school science and technology curriculum look like in order to prepare our students for post-secondary opportunities in these spaces? And I'll start with Mr. Bhatia, if that's okay.
Thank you, Representative Bowman. And it's a personal passion of mine as well. K through 12 is an area that Micron has focused considerably on in the communities where we operate, including Boise, Idaho, where we have our Research and Development Center of Excellence, and in Manassas, Virginia, where we also have tremendous manufacturing capability. And in terms of K through 12 specifically, we have been working to develop STEM curriculum starting at a very early age, and including being very inclusive to underrepresented groups who normally wouldn't have the opportunity or in the past haven't been able to have the opportunity to pursue a path in engineering or into semiconductor capability. So the types of curricula that we encourage are, of course, around science and math, but specifically around data science, because the world of semiconductor manufacturing is getting more and more complex, really unlike any other manufacturing process on the planet. And so you really have to have both strong technical knowledge and scientific knowledge, but also understanding and appreciation of data and data science so that we can operate these highly complex manufacturing facilities very productively and with high quality and very, very low defectivity.
Thank you so much for that concise answer. Dr. Chiang, can you also jump in and just comment on that, please?
Thank you, Congressman Bowman. And I would just supplement Mr. Bhatia's answer with two more points. One is that universities also have a responsibility to work with K-12. For example, Purdue President Mitch Daniels started 3 Purdue Polytechnic high schools throughout the state of Indiana. And we just graduated the first class of senior students. And these are minority serving high schools focusing a lot on STEM capabilities. And second is that there's a mindset of problem solving at this early age of education. It's not just about how much we cover in material for the high school students, but how much we allow them to uncover for themselves, more about their curiosity and their ability to learn. And that is fundamentally the point of education, especially for engineers, is ultimately the problem-solving mindset that we can start installing in their minds at high school age.
Thank you so much. Dr. Chiang and Mr. Bhatia, I would love to follow up with my office to continue this conversation. This is an issue that's near and dear to my heart. And for me, it's a priority for us to create pipelines, K-12 pipelines in historically underserved spaces. I believe it will take our economy to the next level and ensure that no other country can compete with us, because we will finally invest in equitable ways across our country. Thank you, Madam Chairwoman. I yield back.
Mr. Baird is recognized.
Thank you, and thank Chairwoman Johnson. I want to also express my appreciation for your leadership on this committee. And, I really appreciate you working with Ranking Member Lucas, and you stayed focused on the issues that I think are relevant to our Science Committee. And then I always appreciate the witnesses being here. I am always intrigued by what I learn, and so I'm sure that other people feel the same way. But earlier this year, I offered an amendment that would have allocated about $600 million to the National Science Foundation to support the R&D funding for basic research. Unfortunately, that didn't pass. But I really have a strong affinity for basic research, and I recognize how difficult it is to determine what basic research is important today that down the road becomes increasingly important or provides information essential to our society. So, Dr. Chiang, I'm gonna start with you, and would you mind speaking to the role that basic research and funding for the NSF plays in supporting the development of semiconductors that will be needed for cutting edge technologies like artificial intelligence, quantum computing, and 5G? So if you would care to address that, I would appreciate it.
Thank you, Congressman, and thank you very much for your service and leadership in representing our district in Indiana.
Thank you.
I would like to echo what you just said, that the National Science Foundation, just like the Department of Defense, Department of Energy, and many other agencies of the U.S. government, plays a unique and important role in continuing the long tradition of American creativity. Now, in particular, we need a collection of fundamental research, often funded through the National Science Foundation, along with translational research, sometimes funded through other agencies, to work hand in hand together. NSF also funds quite a number of scholarships and fellowships, and we need more American students to be interested in pursuing STEM degrees at undergrad levels, and those with an undergrad degree, say in engineering, would choose to continue to study for a master or PhD degree. I know that they often are tempted by outstanding offers from industries such as leaders like Intel and Micron, but also we do want to incentivize and encourage a much larger number of them to stay on and pursue a graduate degree. And the National Science Foundation plays a critical role. And I hope that there will be many more graduate fellowships to a diverse population in this country in areas related to semiconductors.
Thank you. So would it be fair to say that one of the things I see from this committee standpoint and from federal investment or taxpayer dollars invested, that that some of the basic research that's conducting private industry cannot really justify, so we could start the needle moving early on, and then industry picks that up. We talk about the public-private partnership. Is that would you say that's a correct analysis of this situation, or?
Yes, sir. And I'll give one concrete example. There's this so-called valley of death coming from fundamental advances into commercially impactful deployable solutions. And one way to bridge this so-called valley of death is to create and upgrade existing facilities. For example, in semiconductors, we talk about two dimensions. One is the dimension of the feature size, and it's getting smaller and smaller, down to 3 nanometers these days. And the other is the size of the wafer. And we are looking at 8-inch or 12-inch, and we have a substantial lack of 200 millimeter or 8-inch wafer production facilities in American universities. By upgrading some of those, including possibly here in the Midwest, but in several regional nodes, that will open up a pathway of translation from fundamental research to industry relevant solutions.
I'd like to add one thing if I could. That's one of the things that the National Laboratory Centers do, is work on these concepts that are still not ready for commercial production because they're too risky. And as long as we're working closely with industry on what they want to do, we can develop in these centers things to take the risk out, and then it's ready to actually move to a profit-making organization.
I would like to echo support in that the role in pre-competitive research is absolutely critical and can feed into industry.
So, Madam Chair, I see that I'm out of time, but I could go on for another hour here, and I'm sure you don't want that. So thank you. I yield back.
Mr. McNerney is recognized.
Well, I thank the chair. Ms. Johnson, Bernice Johnson, you've shown tremendous leadership over the years since I've been here. We're going to have a hard time finding a successor to fill your shoes, but I also thank the witnesses. This is an important issue for the future of our country, and I'm going to take this in a slightly different direction. Semiconductor manufacturing does use massive amounts of both energy and fresh water. We need to increase domestic manufacturing without being susceptible to supply chain disruptions. But at the same time, we have to balance the resources needed by local communities. And this has a bearing on the reliability of the supply chain. Dr. Kelleher, Intel has a presence in semi-arid Western states and broke ground on 2 new semiconductor fabrication facilities in Chandler, Arizona this year. Meanwhile, a multi-year mega drought has caused water shortages across the West, a trend that is expected to worsen in the coming decades. What steps has Intel taken to improve water efficiency of the semiconductor manufacturing process and to reduce the impact of the facility on local water systems?
The overall water conservation and reuse of water is a key aspect of all our technology development and within our overall manufacturing sites. To date, we have 90% of the water used restored to the environment, and we're heading for a path, and we've given ourselves a very clear goal, which we're working towards, to be 100 by 2025. 100% restoration to the environment, and by 2030 we're aiming to be a net positive. Not only do we do a significant amount of work in our facilities in terms of water reuse, we also work with the communities in terms of water restoration, and we have several projects in the Arizona region where we've been working with the communities in terms of water restoration. We spend significant amount of money in our facilities to actually help and drive and enable this. So it's a key aspect of our overall development and manufacturing, our footprint, our water footprint, our climate footprint, our use of electricity, and our use of green power. So this is a very important aspect to us.
Well, thank you, and I'd like to see the information that supports that.
Absolutely, I will provide it.
Very good. Mr. Bhatia, Micron has the same issues. Would you respond to the same question?
Sure. So thank you, Congressman McNerney, and agree this is an incredibly important issue for all of us everywhere around the world. And Micron has made strong commitments, including a commitment to spend $1 billion over the next several years in capital investments to be able to reduce our carbon footprint through emissions program reductions, to be able to increase the utilization of renewable energy, to be 100% utilization of renewable energy in the United States by 2025. We're working to be able to reach 100% water reuse by 2030 on a global basis. And we're also working to reduce waste to landfill in all of our locations around the world as well. So we have a very focused commitment on all of these areas.
Okay, well, we need to get to sustainability. Dr. Witherell, I certainly appreciate the national laboratories. I've been to LBNL and Lawrence Livermore and Lawrence Berkeley Lab several times. But I know you are conducting cross-cutting research on the causes and impacts of the drought. Has the labs devoted any resources to improving the water efficiency of semiconductor manufacturing?
Well, first of all, we have the National Alliance for Water Innovation here, I should say, that's actually working on the reuse of water and how to reuse it for purposes But in general, where we actually are putting most of our priorities is how to develop semiconductors that are more energy efficient, which is actually has the biggest leverage on the environment. And that's something that much of our research is doing at the moment.
Okay, thank you. I'm concerned about what happened in Taiwan this last summer when the manufacturing was forced to shut down and tank in water, and that put the whole system at risk. Is Intel taking steps in the U.S. plans to increase resilience against water shortages?
Absolutely. We are constantly looking at our water use and working to reduce our water use and overall reuse of the water that we use. So, yes.
Okay, thank you. And I'll yield back.
Mr. Webster is next. You're muted, Mr. Webster.
Thank you, Chairman and Ranking Member, for putting together this forum. This has really been excellent in the dialogue and also even just in the review we're doing of some of the things that have already passed. I know I understand to build a foundry is about $10 billion, and I heard later here on this panel that it's maybe $15 billion or more. It's getting into real money, and so I would ask you, Dr. Kelleher, if you could kind of elaborate on what you think is the maximum amount we could do with the money we've given to this program that we could do as far as foundries, and are you also in agreement with what was said before, that these sub foundries are scattered around would be even better way to do it? Is that true?
Well, first of all, I agree with the numbers, and I know Manish was speaking about the numbers of building the facilities. It's anywhere 15 to 20 billion, and the amount that's spent on a given facility obviously is very much dependent on the size of the facility. Overall, we've been very clear, we're opening our fabs up for foundry here within the United States, and we're opening up for overall from our foundry so that we can open up the use of our fabs to basically the fabless designer of the fabless companies, so that we can make foundry available here within the United States. I think overall, I would take us back into the two pieces of where we spend our money within from the CHIPS Act. I think we have to focus on R&D in terms of enabling our future, because that is the long haul and that's the long building of our future. And then there is the building of our overall US manufacturing capability. And that, I believe, we need to continue to do. If you spread the money too much, then you actually won't end up getting, I would say, an overall effective bang for the dollar. But it becomes the appropriate spreading of that money so that we can overall grow our foundry industry here within the United States and keep moving our leading edge R&D.
Yes, well, would these foundries be focused on advanced semiconductors?
Intel is focused on advanced semiconductors. Back in July, I released our overall roadmap for the next 4 to 5 years, and these technologies within Intel are available as foundry technologies. And yes, is the answer.
Yes, I've always been an admirer of Intel. And I thought it was interesting. How do you know which direction to head? I mean, there's a lot of directions that can happen. How do you focus in on just the amount you would play in, or the ones you would have?
May I clarify the question when you say how do we focus in? How do we focus in from a technology development, or is it a broader question?
No, it'd just be the technology component.
And so there are many aspects in terms of feeding the overall pipe from the technology. There is the long-term 5 to 10 years out. There's a lot of items which are in the pipeline. We do research internally with Intel, but there's also research done in the universities. Slowly, as you progress over time, there's a filtering out in terms of which are the more likely candidates that will be successful for the future. And out of that filtering, then it's proven at the first level of concepts. Then we take it into development, and in that development, we actually prove out that we can take it from the lab to fab concept, and that will be enabled for high volume manufacturing. So it's a 5 to 6 year process in terms of going from the concept of an idea to actually showing up in terms of a volume manufacturing. And sometimes it can be much longer than that, depending on the aspect of the technology that is being developed.
Okay, so so you would be developing a component of a machine of some sort, i.e. a mini computer or something like that. You would not be developing something for someone else who's building it. You would be developing something and someone else would use it. Is that
Correct. We developed chips, and we sell packaged chips, package designed, to other customers who then use those packaged chips, basically the microprocessors, to build other products. Similarly, memory goes into those packages as well and goes into those products. So we're providing either wafers to our customers through the foundry, or packaged products, packaged microprocessors to our other customers.
And, I'll ask one more. It just sounds like that it's billions of dollars to build, so that there's this cost of building these foundries, but also I assume it takes time to do that, and we may not have that time. Is there ways to take existing infrastructure and sort of meld them into this process so that we use the facilities we have, but also are building new foundries at the same time?
I think time is of the essence. But one of the key things that I said in my testimony is that I believe we should use existing infrastructure within the business, within Intel, Micron, within the other US semiconductor companies, so that we can shorten the time to get and basically reduce the cost. And thereby, then, if we do big challenges across us as a number, as across the industry here in the United States, using as much as possible of our existing infrastructure, that will allow us to get to results faster.
Thank you very much. Yield back.
Mr. Tonko is recognized.
Thank you so much. Chairwoman Eddie Bernice Johnson, thank you for the strength that you've brought this committee. I, for one, appreciate your leadership style and your accessibility to myself and our colleagues. It's just a good strength and a very important committee, and you've led it masterfully. So thank you, and look forward to the next year where we can continue to get good things done. So I thank you and Ranking Member Lucas and our witnesses for joining us today for this very important hearing. The United States has long been a global leader in the research and development of semiconductor technology. In fact, New York's capital region that I represent has been home to trailblazers in this industry for now over 2 decades. So partnerships amongst our academic institutions, our regional industry, and government have enabled major breakthroughs and innovation in microchip technology. As our reliance on microelectronics in everyday life grows, it is critical for us to leverage strategic investments across government and industry to sustain our nation's long-term economic and manufacturing competitiveness. You may be aware that this committee is currently examining ways to elevate DOE's role in the national microelectronics R&D effort. I'm working on legislation that would leverage DOE's capabilities, including the national labs and their partners in industry and academia, to tackle foundational challenges in the scientific areas relevant to microelectronics. Such an effort would be separate from, but complementary to, national semiconductor technology centers and would involve a broad-based research program as well as a more focused center-based effort akin to the national quantum centers. With that being said, Dr. Witherell, would you support such an approach?
Yes, Congressman, thank you very much for your question. And if you look at my testimony, it makes many of the points that you bring up in the Micro Act. And so I'm very strongly support that, especially the foundational role the DOE and the laboratories have in developing these underlying sciences and engineering that underpin our development. And Dr. Kelleher said the right thing before. The advantage of the U.S. is to move faster than the other countries. That's the only way we're going to win this. We're not going to win it by beating them at bulk manufacturing. It's to be faster. And part of that faster is getting back to where the investment on the federal side was more in keeping with the large investment on the private side, so that we could engage this in the right way and do the pre-competitive things that are best done in national laboratories and for the industry.
Well, thank you. And the expertise that's housed at the national labs, if we could focus on that, what can that expertise contribute to our national effort to leading in microelectronics development and production?
Well, let me take one example. We've been bringing artificial intelligence to use for advancing science faster, how you accelerate the cycle of trying new materials, see what works and do it. You can do that faster in artificial intelligence than you can do it in the laboratory at times. So we have a materials project, which is designed around actually sorting through materials and seeing which are the ones that have the right properties faster than we've been able to do it in the laboratory. We have many examples like that.
Mm-hmm. And how would you see this feeding into an effort like the NSTC, which would presumably be more focused on later stage technology development?
And I think the role for example, DOE centers in this is getting through concepts faster to take the risk out and see which are the ones more promising for developing to the scale that you would have at an NSTC facility. You have more ideas feeding into that central facility.
Thank you. And can the Department of Energy play a complementary role to advancing microelectronics R&D?
Well, yeah, go ahead.
No, and I was going to encourage anyone else to offer comments too, but let's hear from you.
Well, I just say we have this longstanding connection with the industry and how to best serve their purposes. And I think it's just finding out how to continue that into the new technologies that are developing for the future.
Yeah, any other comments from our other panelists?
No, I think I'll just echo the comments that Dr. Witherell made, that continuing to have advanced funding into advanced foundational research through the existing programs with the universities and the national labs, is paramount, and that we do believe this network of decentralized technology centers can help with bridging the gap from those university and national laboratory environments to mass production by allowing industry consortia to leverage existing resources in the ecosystem to accelerate that time to market.
Thank you very much. Well, I see my time has been used. I don't know if anyone else had a comment. Perhaps you can send it in written format to the committee. But with that, Madam Chair, I yield back.
Mr. Garcia is recognized.
Yeah, thank you very much. And to our witnesses, thanks for taking the time. Very educational and enlightening. Obviously, we have a challenge in our hands. My first question is geared towards Dr. Kelleher and Mr. Bhatia. For your respective companies' chip sector or chip divisions, what percentage of the bill of material for your products is coming from China? Dr. Kelleher, you can go ahead.
I will start with the majority of our manufacturing is in the United States.
Yeah, the manufacturing, I understand. What about the bill of materials? Where are we sourcing product, whether it's a rare earth material or any sort of elements that build up to your larger assemblies?
We source our rare earth materials and our resources worldwide. The precise percentage I will need to follow up with you.
I would appreciate that. I think that's important for us as a nation to understand what level of dependency we have in this very critical, what's effectively an Achilles tendon right now in terms of technology and capability. We have to characterize what percentage of the bill of materials is actually also coming from China. Mr. Bhatia, do you have any idea from a Micron perspective?
Sure. So I'll echo that. Rare earth materials, as you point out, are an area of weakness in the global semiconductor supply chain. We do also, as Intel does, source those globally. However, there is, as an industry, a strong reliance on China for those rare earths. So it's not so much the percentage of the bill of materials, but they are essential elements for many of the semiconductor processes. And so we have been actually working with members of the U.S. government to encourage programs that would allow for exploration and mining and economic incentives to encourage production of rare earth materials to be done in other areas around the world to increase the supply chain resiliency of those. With regard to your other question in terms of the total bill of materials in China, I'll have to get back to you. I would just say that the semiconductor manufacturing bill of materials is largely driven by the equipment and the precision and the specialty chemicals and gases. So that's not so reliant on China other than these rare earth materials. However, assembly and packaging, those other lower value added portions of the manufacturing process, those are areas where China has a large role, but there are multiple other areas where we source those packaging materials from across Asia.
Okay, thank you. And again, let me just be clear. I'm not asking this, to point fingers or to attribute fault. But I do think that with just like any other major problem we have, the first critical step is self-awareness and characterizing where our weaknesses are. So I would appreciate if you guys could follow up with sort of a bill of material breakout by whatever metric, whether it's cost, just part assembly percentage, or weighted dependencies by country, though, if we can, just to get a sense of where we are dependent, especially with regards to China. My other question for the two companies as well is what percentage of your revenue in this sector is coming from military applications versus just commercial applications?
Well, I will need to follow up with the precise number in that. We do support the US government in certain projects, and I will need to follow up on that, but overall we do support.
Thank you, Doctor. And Mr. Bhatia, any idea on yours?
I'll have to follow up as well. We certainly do support the U.S. government, and we do see that memory, both DRAM and NAND, are increasing portions of military applications as they are with multiple other industrial and automotive applications as well. The bill of materials portion of those systems, advanced systems or advanced products, continues to grow with regard to DRAM and NAND flash technology.
Okay, yeah, because I think it's critically important that while the big companies and the big folks in the room are going down range with this overarching chip challenge, we can't forget that there is also a military application to a lot of these things that have different requirements. And while you're receiving government funding for things like the foundries and the R&D that goes into it, you need to have still connective tissue to other government agencies like DARPA, IARPA, ARL, NRL, to make sure you're baking in those requirements into your early design, and then also partnering with small companies that are specializing in these applications. And there's several out there. Happy to get you a list of those if you don't already have them. But we can't do these massive investments only to solve the commercial problems and then realize that we are still extremely vulnerable on the chip applications on the military side. And I think you guys would all agree with that. I think we just got to synergize across multiple agencies and the small companies as well. With that, I'm out of time. I yield back. Thank you.
Ms. Wild is recognized.
Thank you so much. I appreciate this hearing and the opportunity to elevate an issue that affects workers and businesses in my district, which is Pennsylvania 7, the Lehigh Valley of Pennsylvania. My community is home to many, many manufacturers, and I hear regularly from companies in a range of sectors about how the shortage of chips, such as has been discussed today, is affecting their production and their ability to regularly schedule workers. One auto manufacturer, Mack Trucks, has faced production interruptions this year, an unneeded complication. And by the way, they have plenty of demand. It's not for lack of demand, but it's been a threat to some of their innovative work in spaces like zero emission heavy duty trucks, exactly the type of advances we want America to lead in. We know the drivers behind this supply chain crunch are varied and largely connected to the pandemic. And I was proud to support the CHIPS Act last December. But a year later, here we are. We need again to take bipartisan action on this urgent need and provide the appropriations for this law that the Senate has moved, as well as address some specific needs like automotive grade chips. It's about the American economy. It's about good paying jobs across industries, and it's about our national competitiveness and security. So with that said, my first question is for Dr. Chiang. In your testimony, you discussed some specific partnerships on microelectronics in Indiana. We have spent some time in this committee discussing geographic diversity of innovation. In July, the committee reported out my bipartisan Regional Innovation Act, and we are working to get that enacted as part of a larger competitiveness package. But that bill was technology neutral. What do you see as the role of the microelectronics in the geographic diversity of innovation?
Thank you, Congresswoman. Indeed, time to act is now. There is a sense of urgency, and this is key to our national security, economic security, and job security, because many other industry in the digital economy depends on their access to chips. Otherwise, they will be furloughing employees whom they would happily be otherwise paying overtime. And I also highly appreciate, Congressman, you're highlighting the importance of being inclusive across different communities and diverse in the geographic locations. What we need in education and in R&D is a distributed network of many different parties. Here in the Midwest, for example, in my home state of Indiana, we have an abundance of customers, including automotives and medical electronics industry. We also have an abundance of a workforce that still retains the manufacturing DNA. These semiconductor fabs, they are fancy, expensive, important factories. They are the factories of the future. And we have those manufacturing DNA in states such as Indiana. And thirdly, if you look around the drivable 5-hour distance from where I am right now in West Lafayette, Indiana, you will see extremely high concentration of high caliber universities, as well as community colleges, serving an incredible number of American students. So I believe that, yes, we should emphasize on the inclusivity and the diversity of geographic locations and make sure that all parts of America get to benefit from and contribute to the resurgence of semiconductors.
Well, you must have read my mind. My district is one that is rich in higher education. We have 6 four-year colleges with graduate programs. We have 2 unbelievable community colleges. And one of the things I'm particularly interested in is knowing how universities and community colleges can partner with states and local industries to capitalize on regional strengths so that we can contribute to the domestic microelectronics supply chain. I'd like to know whether you or anybody else on the panel would like to comment on how universities might go about doing that.
Let me say one thing, that the user facilities at the national labs, I'll take Brookhaven National Lab as an example in New York, where you have these nanoscale centers. They are user facilities that work with every university in the country in those, providing, in some cases, providing facilities that those universities can't themselves afford and making it available so these university researchers can develop their skills.
And I concur with Dr. Witherell that there are facilities such as the Berkeley Nanotechnology Center, which has the largest and cleanest clean room among all American universities here at Purdue. If we could upgrade it to be producing at the 200 millimeter scale of the wafer and open that up as a hub, a regional hub for other universities, for community colleges, and for industry partners to come together. That would become a very effective bridge for the country and for the region between the workforce dimension and the R&D translation dimension of the problem.
Well, thank you for that. I'm out of time, but I'm going to ask my team to follow up on that with you, because it's an area that I think my district is in many ways uniquely situated to address this issue head on with this merger or this alliance of higher ed and industry. Thank you so much. Excellent hearing.
Yes, ma'am.
Ms. Kim is recognized.
Oh, thank you very much, Chair and Ranking Member, for hosting this hearing, and thank you to our witnesses. I know the Senate and the House is now trying to work on, proceeding with the conference process to, hash out some of the differences between our two chambers. And as we do, I wanted to ask to any panelist, what, in your opinion, are the top 2 or 3 areas of focus where the U.S. government should invest $52 billion? That was included in the Senate-passed U.S. Innovation and Competition Act in order to have the greatest sustaining impact to achieve our goal of American innovation and competitiveness in the industry.
So I can start. I can just reiterate, Representative Kim, that as was mentioned, the cost of semiconductor research and development and the cost of building large-scale semiconductor fabrication facilities continues to go up and is very, very large. And so definitely feel that the prioritization should go towards leading-edge research and development on technologies that will be able to be in production for many, many years into the future, as well as leading-edge manufacturing fabrication facilities. And definitely believe that we should be focusing on the technologies that will ensure American leadership in microelectronics well into the future. And with the rate of change of technology being the defining characteristic of our industry, every 18 to 24 months we introduce new technologies. We need to make sure that that these investments are made with an eye towards the future, and also that as we think about these investments, we understand that there will need to be even extended future investments to keep ourselves on the leading edge.
Thank you very much.
I would that as well, in terms of first focusing on R&D and including and ensuring that our IP is developed and maintained in the United States, and from a leading edge perspective, and then expanding the fab capacity to support the growing demand. And also we cannot forget getting advanced packaging capability and capacity back here very clearly in the United States.
Thank you. I
would echo that.
Yes. Would you like to say something, Dr. Chiang? Go ahead. Dr. Chiang, go ahead.
Yeah, thank you, Representative Kim. I will echo that by also highlighting that the ultimate supply chain in semiconductors is the supply chain of human talent. And we need to substantially invest in the human talent pipeline. Otherwise, we'll have hundreds of billions of dollars worth of public-private partnership and the best facilities throughout the country, and yet not adequate number of engineers to staff and operate them. And there is also the need to ensure the connection between policymaking and the investment. The policy implications to domestic and foreign policy is tremendous. And that's why at Purdue, we launched this year the Center for Tech Diplomacy at Purdue as a think tank specialized at the intersection between technology and foreign policy. And I believe that the USICA bill and the CHIPS for America Act portion of it will be critical win if we could indeed fund and appropriate that as soon as possible.
Yeah, and I see it's really supporting the whole ecosystem, and it really is all the federal science agencies have to be engaged in this for this to work. It's that big a problem.
Thank you. Thanks for mentioning that, Dr. Chiang, because I was, during the markup, I was successfully able to include an amendment in the NSF with Future Act and NISP reauthorization related to STEM education. That leads me to the next question of, if any of you can touch on how much the decline in the supply chain or anything can be attributed to the workforce development issues you mentioned, and what is the role of STEM, high-skilled and technical education in the semiconductor industry's workforce recovery?
Well, I'll start, Representative Kim. I believe maintaining basically an educated workforce and the supply of the workforce so that we can continue to grow our industry here within the United States is absolutely critical. To this point, we have been with universities and with the various colleges have been able to source with a lot of work, have been able to support adequate talent and resources, but it is becoming increasingly challenging. So that is absolutely going to be critical going forward to maintain the supply so that we can continue to resource the work going forward, particularly as we want to grow and expand.
Yes, and I'll just add. Thank you for asking that, Representative Kim. In addition to the focus on university talent and graduate school talent for our leading edge scientists for R&D and innovation, there's also the factories of the future are not like the factories of the past. Factories are becoming far more automated, far more complex manufacturing processes. We're utilizing artificial intelligence, machine learning, and big data to operate all of these leading edge facilities to make them productive, to maximize the quality levels and the output that we're able to get from these facilities. And so the training really needs to be also for the skilled trades who are working in these factories. We need to be looking at, in addition to STEM education, reskilling of those from other industries. We need to be looking at reskilling of those with military background towards the technologies and the capabilities required to operate and maintain these mega fab clusters for semiconductor manufacturing.
Thank you, all the witnesses, for your responses. I know my time has gone significantly above, but thank you. I yield back.
Mr. Caston is recognized.
Thank you. Thanks so much to all our witnesses. It strikes me that like so much of what our economy is seeing right now and all these constraints we just have these huge supply-driven constraints. We saw the Texas freeze shut down a bunch of refineries and is tightening gas markets. We saw a huge collapse in new rig production that's tightening up our natural gas markets. And of course, a big part of the reason we're here today is because we had a drought in Taiwan that slowed up some production capacity there. And of course, that same Texas freeze slowing up capacity. Mr. Bhatia, I see you nodding your head. I'm delighted we're having this, and I'm delighted for all the thought you've put into trying to think about how we address those supply constraints in the system. But I have this nagging concern about the demand side. If I understand it right, an electric vehicle needs about 2,000 semiconductors, which is roughly twice the number of a non-EV, and EVs, which is great from a climate perspective. As an EV owner, it's great from a fun to drive perspective. There were 10% of new vehicle sales last quarter, so they're surging. And I guess I'll start with you, Mr. Bhatia, because I see you nodding your head. As we continue that modernization of our vehicle fleet and all the good things, we don't want to slow that down. What is that going to do to the demand for semiconductors? And even if we got rid of the current bottlenecks in the system, how big a deal is that in terms of the total demand balances?
So I think automotive, well, thank you, Representative Caston, for asking this question. And, for today, the automotive sector is not a huge consumer of memory or storage. However, it is, for Micron, the fastest growing market for us as we look forward into the next decade. As I mentioned in my prepared comments, the autonomous vehicles of the future are really going to have as much content as a data center does today. Even semi-autonomous vehicles will have as much in the next few years, will have as much content as full-blown servers do today. And so what this means, in order to ensure that we're able to keep up with this strong demand surge, takes careful long-term planning. And as you were describing the supply shortages that are plaguing multiple end markets today, with automotive being one of the primary ones. I think it's worth noting that the memory industry, and Micron in particular, has not really been the primary bottleneck for the industry. And that's because the memory industry and we as a primary player in that industry plan over a long period of time how much capacity we think we need in line with the long-term demand trends that we see. And that's why it's so important that the CHIPS Act and the refundable investment tax credit gets implemented with urgency, because it's going to allow us to make sure that whether it's for logic or whether it's for memory, we're going to be able to have long-term investments that can be made to prevent these kind of shortages from happening in the future.
Well, thanks. And if I'd love to hear from others if you have thoughts that are contrary or otherwise to that, but I know I'm a little bit tight on time here, and I want to move to Dr. Kelleher quickly. We've had these, as I mentioned at the start, we've got this plant in Taiwan that, we had a drought and a water issue, if I understand right. We had these plants in Texas that had the Texas freeze and slowed them up. To what degree have you been thinking at Intel, should we be thinking about how to weatherize the supply chain of our chip industry in response to an increasingly volatile weather system? Because climate change ain't going away and it ain't slowing down. I wish that wasn't true. But to what degree is the supply chain as weatherized as it could be, and what can we do to improve that?
Well, I'll start speaking about our Intel's factories, which is basically starting from manufacturing the silicon. We have very active, when we're selecting our sites, and this has been true over the last 30 years, we have a very strict criteria in terms of what can the environment or what could actually impact our factories to continue to keep running on an ongoing basis. We also spend quite a lot of time evaluating our facilities' infrastructures themselves, and we invest quite a lot of money into the facilities themselves so we can robust ourselves against snowstorms, we can robust ourselves against all the various aspects that in terms of from an environment that can go wrong. I think across the supply chain overall, one of the key things across the supply chain is I truly believe we should have no single points of success. I call them single points of success rather than single points of failure. But I think we truly need to look as an industry and continue to keep working that so that we continue to have not single points of success, that we can robust ourselves against unique our environmental impacts, that our ecosystem impacts that causes, I would say, a continuity risk of keeping the supply chain running.
See, I'm out of time, but thank you so much, and I yield back.
Mr. Feenstra is recognized.
Thank you, Chairman Johnson and Ranking Member Lucas. Chairman Johnson, I just wanted to say congratulations on your upcoming retirement. And after a long and admirable career in public service, I truly admire all the work that you've done working on a bipartisan basis. I also want to thank each of the witnesses for their testimony and sharing their extensive research and experience with us. This question is for Dr. Kelleher. I understand that most advanced semiconductors are currently being manufactured in Taiwan. As you know, there is concern that China may eventually attempt to invade Taiwan and take ownership of its semiconductor expertise. We've already seen examples of the CCP poaching Taiwan's talent and intellectual property. Can you please speak to the importance of securing IP and semiconductor expertise from this uncertainty? How would the programs in CHIPS Act support this endeavor?
Well, I'll start with, first of all, I will start with saying that back in July, I outlined from Intel our path back to where we get back to overall leadership from a process perspective, and we're aiming to get there in 2025, and we're spending pretty significant investment in that happening. One of the key things that I think we needs to be, and I have said this in my testimony multiple times, as I've been talking about this, is maintaining the IP within the United States. I think it's absolutely critical for United States leadership in semiconductor leading edge that we maintain critical IP for that within the United States. Then all of us have the appropriate policies in terms of protecting that and how we ensure that that IP maintains within the United States. But I think within this work, within this overall CHIPS Act and within this overall funding going forward, we need to enable that.
Thank you so much for those comments. I greatly appreciate it. Dr. Chiang, in my district, we're home to Iowa State University, which houses a Microelectronics research center, which is doing fantastic work in developing new materials that could transform the speed and efficiency of computing and increase the production of sustainable agriculture. Universities will be crucial to increasing domestic microelectronics manufacturing to ensure that we have adequate jobs and a skilled workforce that can fill these jobs. How can industry and universities work together to provide support in developing a stronger practice-oriented programs and provide necessary research and education laboratories for these essential infrastructure and for training that could be appropriately made?
Thank you, Congressman, for the question. And indeed, it is essential for universities of this country and the private sector to work very closely together. There are three broad lanes. One is R&D collaboration. One is workforce, not only recruiting, but development together through internship, through upgrade to facilities, and through online learning. And the third is co-location, economic development that creates knowledge and jobs together, that creates the positions to be filled and the talent that can fill them. And in this regard, here in my home state of Indiana, Governor Holcomb and his team, and Secretary of Commerce in our state chambers, have been working very closely with universities such as Purdue to create that economic development engine. And I think that in addition to R&D and workforce, by co-locating physically factories of the future, along with the workforce of the future, that is the best way to both develop talents and to develop the manufacturing capacity. Over.
So, Congressman, I'd just like to add to the fact, of course, that Ames National Lab at Iowa State is also a very important contributor in this, and their Center for Critical Materials. So let me call out a close partner of ours.
Yeah, well, and I just wanted to comment on that, Dr. Witherell, that, they lead the efforts in graphene research, quantum material discovery, and critical materials. And quantum materials holds promise for quantum computing, which I'm very passionate about, but also next generation information storage. How do you see graphene and quantum materials enabling the next generation of microelectronics?
Well, I think this is part of the role of the national laboratories, because we don't know which of these materials will end up winning the game a few years from now. This is a very fast-moving thing. And so we need to have these laboratories that have the scale and R&D capacity to try these things and find out which of the ones are low risk enough to be translated over into industry. That's what our job is.
Well, thank you so much for your comments, everyone. I'm really excited about this hearing, and I yield back.
Mr. Foster is recognized.
Thank you. Am I audible and visible here?
Yes, you are, sir.
Great. Well, first, I just want to also echo my congratulations to our chairwoman on her pending retirement. She has a lot to be proud of in her service to the Science Committee and to our country. And although I'm probably best known as being Congress's strategic reserve of physicists, I've actually had a parallel existence in my career with integrated circuits. And when I worked for one of our witnesses today, Mike Witherell, when he was director at Fermi National Accelerator Lab, I was still very involved in custom integrated circuit design at Fermi Lab, where back in 1989, I had invented a type of specialized integrated circuit called the QIE, a charge integrator and floating point digitizer that's still being developed and used in high energy physics experiments. And it's probably been implemented in 10 increasingly advanced mixed analog digital IC processes. So I'm stayed a little bit current on the incredible advances there. But before that, actually, when my little brother and I started our company back when I was 19, our very first prototypes were hand-wired using the Intel 8080 microprocessors and the Intel 2002 static RAM. And when we needed an order of magnitude increase in computing power, we chose the Intel digital signal processor chip. And when we finally got our first production order and needed an office and an actual factory, we chose as our telephone number one ending in 4116, named for the MOSTEC MK4116 16 kilobit dynamic RAM capacity, which seemed infinite at the time. So our company's now been successful, has over 1,300 employees, manufactures about 70% of the electronic theater lighting equipment in the US. And we've kept all those manufacturing jobs in the heartland, which is something I'm very proud of. But because of the current chip shortage, at this moment, most of our engineering staff is busy not designing new products, but on redesigning existing products around chips that can actually be purchased on the open or gray markets, and trying to understand the massive misallocation of capital, where somehow whoever it was that was running the financial operations of our economy generally, and specifically the big manufacturers, saw, somehow our financial system is more interested in speculating in Bitcoin than building IC fabs, and trying to understand how do we deal with that, the incentives that led to that misallocation of capital. And so my question is, first for Mr. Bhatia, did you really say that there were 176 mask layers in an advanced flash product? Did I hear that correctly?
Not mask layers. First of all, Representative Foster, I congratulate you. And if you want a job, I think we definitely have a few open positions. So that would be terrific if you want to come back to our industry.
You need someone with less gray hair.
I don't. It sounds like you're plenty experienced. 3D NAND flash technology several years ago stopped scaling in the X and Y dimensions and began scaling vertically. So we actually stack 176 layers of NAND flash devices, active NAND flash devices on top of each other.
Okay. So these are physical stacking. That's the 176.
Yes.
Okay.
Yes.
That
was all monolithic stacking that happens in fab, but this is how
but a smaller number of mask steps. Okay. Yeah. That's less frightening. Now, there's a narrative about commodity products such as DRAM. And there's something that the U.S. somehow cannot and should not compete in. And I want to congratulate Micron for not buying into that narrative, but obviously it's been a struggle. And I think we have to appreciate that in the unregulated and unsubsidized free markets, this subjects commodity manufacturers to a huge boom and bust cycle. And so either we have to just grit our teeth and say we are going to occasionally interfere in the free market and effectively develop one or two national champions in this technology, or we have to just say that's the free market. Only the fittest survive, only the paranoid survive. What's your best thoughts on that? You had mentioned actually that you don't think some iteration of the technology consortium would work these days, just because they're realistically only two U.S. champions of IC process development. Yes. How do we make that decision?
Yeah, so I think the first thing to recognize about memory, and by the way, I appreciate your recognition on the 4K MOSTEC device. That was many of our first DRAM devices. Memory is essential to all computing environments, and it really is going to continue to grow in content, whether you're talking about artificial intelligence in the data center, 5G in phones, or autonomous vehicles in the future. Continue to be central. And actually, memory technology accelerates at the fastest rate in the industry. And we're challenging the laws of physics on every single generation of DRAM or NAND flash. And so, we do believe it's an essential component of the semiconductor strategy for the United States, and investments do need to be made there. And really, technology and leadership in technology like Micron has achieved, as well as high volume manufacturing and excellence in productive, smart manufacturing environments. These are the two core areas that we need to be investing in as a country. And of course, Micron very focused on, because these are the core elements of competitive advantage in the memory industry. So I actually encourage that the memory is considered to be very strategic as part of the CHIPS Act and the investment tax credits that are being considered unfold.
Yeah, and let's see, am I out of time here? Did someone give me a quick estimate on the time, because it's reading 0?
Yes, you're out of time, Mr. Foster.
All right. Well, I yield back, and if there's a possibility of a second round of questions, I'd be very interested.
Mr. LaTurner is recognized.
Thank you, Madam Chairwoman. First and foremost, I just want to say, no matter how long the good people of the 2nd District in Kansas send me to back to Washington, D.C., I will forever be grateful for being a part of this committee, not just because of the subject matter has been so fascinating and been so meaningful to be involved with, but because of the incredible example, Chairwoman Johnson, you have set along with Ranking Member Lucas. It's a real example of how Washington could and should function. And so I just want to say that and congratulate you on your retirement, a well-deserved retirement. First to Dr. Kelleher and then to Mr. Bhatia. While the purpose of U.S. government investment in semiconductors is American competitiveness and innovation, working with non-U.S. companies that play a vital role in the supply chain, such as ASML, TSMC, and Samsung, will be important. What do you think is the role of the National Semiconductor Technology Center, if any, in managing the relationships with non-U.S. companies and the U.S. government?
Maybe I'll kick off with saying within the National Semiconductor, in terms of its funding and how it allocates, I think, first of all, I believe its governance needs to be led by U.S. semiconductors and ensuring that the decisions in terms of priorities which are made within the NSTC are truly moving ahead the United States agenda. And also that there is a prioritization given to the funding that ensures the breakthroughs that moves the research forward within that enables the United States. Other companies such as ASML, TSMC, IMEC, all of those other companies, they have their potential roles to play. I'm not saying they're part of the governance, but they have, depending on what are the unique challenges and breakthrough. If I pick ASML, ASML is the unique company that has providing EUV lithography, which is absolutely critical for the world to keep moving on leading edge semiconductors. So I think that IMEC also has one of the world's preeminent research centers. So I think there's an opportunity for us to work to enable that, because the supply chain is quite complex. But I think it needs to be situational in terms of the challenge that's being worked on, rather than an absolute same answer for every project.
Thank you. Mr. Bhatia?
Yeah, so I'll agree. I mean, the U.S. doesn't have leadership in all areas of the semiconductor ecosystem. There's some we don't even have U.S. companies that participate in. And so certainly there will need to be foreign company participation in certain areas. However, there are some elements where foreign participation could create competitive challenges for U.S. companies. And so I agree with Dr. Kelleher that those situations do need to be managed on a carefully and on a case-by-case basis in certain areas.
Thank you both. This is for everyone. So feel free to. We can start with Dr. Kelleher again. In the past year alone, we've seen how environmental disasters can disrupt the supply of semiconductors. In Taiwan, severe drought has limited water availability, leading to production delays. Domestically, Winter Storm Uri created power outages, resulting in a months-long backup in production. How can we create a domestic semiconductor industry that is more resilient to extreme weather, and how can we encourage the same on the international stage?
I'll start with saying, and I go back to a point I made earlier, one of the first things that you need to do with your facilities is to robust your facilities so that your facilities and your supply chain are basically that you have a plan B when plan A doesn't work. You need to robust the facility so that they are actually robust against power interrupts, robust against environmental like weather, snow, storms, haboobs, doesn't matter. When I was running the factories, I've had my pick of environmental. And I also, when I ran a factory in Ireland, I knew every storm that was taking place in the Atlantic, because our slurries and polish, some of our materials were on ships in the mid-Atlantic. So one of the things is it can never be ignored in terms of, we call it our business continuity or our supply chain continuity, That has to be built in, and you need to have a robustness and not single points of success or single points of where you fail. So there's the facilities being built to robust against, I'm going to call it weather and others, but there's also for each of the unique either equipment, materials, etc. How do we have alternate sources? Where are those sources based? Is there enough of a distribution of where they're based? So if something happens in one place, that you have the supply coming from the rest. So it's not a one answer for all. It's quite a complicated piece of work. It takes dedicated focus on it to ensure that your factories can run 7x24 for 30, 40, 50 years without impact.
Thank you, Dr. Kelleher. Unfortunately, I've run out of time, but I look forward to continuing this conversation. I yield back, Madam Chairwoman.
Ms. Stansberry is recognized.
Thank you so much. And Madam Chair, like many this morning, I want to add my voice to the chorus of grateful members who are so grateful for your many, many years of service and your advocacy and your work on behalf of our science and technology enterprise. You will be so missed, and we wish you all the best in your retirement. So thank you so much for your service. And I'm excited to be here today to talk about an issue that is so important to my home state of New Mexico. You know, we're here to talk about semiconductors because they're essential to every aspect of our lives, to the functioning of our modern world, from powering our phones and our electric devices to powering our grid, and the technologies that will help us fight climate change and help to build the new world that we're all working so hard to build. And New Mexico is particularly well poised to help lead the charge here and help to ensure American leadership in microelectronics, thanks to our national laboratories and our commercial scientific industries and our private industry. So we are proud to be leaders in this field that will determine the direction of technologies for years to come. At Sandia National Labs, which is in my district, the labs have made groundbreaking discoveries for decades, changing technology as we know it. Last year, Sandia partnered with IBM to lead the field in research and development of next-generation transistors called gate-all-around nanosheet field effective transistors that use less power and allow for faster computations. These transistors can help us continue Moore's law long beyond what we had previously thought. And Sandia is also working with the private sector to develop memory devices that have nearly unlimited endurance and withstand harsh environmental conditions that outperform current commercially based memory devices on the market. While Sandia has already developed partnerships with commercial partners for these projects, a lot of the work that happens in our national labs, as many of you know, actually never makes it to market. And so one of the things that we've been working on in this committee, and I've been working with my colleague, Senator Lujan, and others who signed on to our bill, which is the Partnerships for Energy Security and Innovation Act, is to create a nonprofit foundation that will help to align the R&D that happens at our national labs with the private sector so that we can bring these technologies to market and really bridge the lab to fab gap that we see in our science and technology enterprise. And once we get those technologies to market and out of the development stage, New Mexico stands ready to manufacture, to assemble, and to test those semiconductors because we are proud to host an Intel campus, one of the nation's leading integrated device manufacturers in Rio Rancho, which is in the greater Albuquerque area. Which announced earlier this year that it is investing $3.5 billion for the manufacturing of advanced semiconductor packaging technologies, which is expected to create thousands of jobs. So, as we've seen during the pandemic, semiconductors impact every aspect of our lives, and I look forward to working with the committee to bring manufacturing jobs back to our country and make sure that we are leading the way in research and development in these critical areas. But I think that one of the biggest obstacles that we face is the development of our STEM workforce. And we see this in New Mexico every day where we have thousands of vacant positions in our national labs, in our engineering firms, in our research entities. And so I think one of the things that's really important, and I'd like to ask Dr. Witherell about this, in your testimony, you note the importance of workforce development to the future of domestic microelectronics. And you point out that this is especially relevant for our national labs, who of course rely not only on thousands of scientists, but also on skilled technicians. And so I wanted to ask you, Doctor, if you could talk a little bit about what you think Congress can do to help foster that STEM workforce so that we are prepared for the future.
Thank you very much. And I will say that we at Berkeley also partner with Sandia on our Quantum Systems Accelerator Center, where we are pleased to work with them. But all of the laboratories are working very hard on developing the STEM pipeline at every stage. Of course, the obvious thing is we have a large fraction of the postdocs working in these disciplines in the whole country are at the labs, and that's producing. But we're also trying to help with undergraduate education and K-12. And the fact New Mexico is a good example of this, where the laboratories there can have a very large impact on that institutional. But it's also true that for the security laboratories, workforce is the lab director's biggest problem, actually. Just to have the workforce to fill the pipeline at Sandia, Los Alamos, Livermore. So all of us are working on how to develop a large and diverse workforce that can feed these things, because in the end, the nation has to go faster than other nations.
Yes, thank you so much, Doctor. And I think you really put your finger on it, which is that we have to be building that pipeline from early childhood education, even through our K-12 system. But we do have an immediate challenge of how do we get more STEM professionals into the workforce and working in our labs and our public institutions to ensure that we're at the forefront of this work. So I really appreciate your words and your good work. And with that, Madam Chairwoman, I yield back.
Mr. Lamb is recognized.
Thank you. And I want to join everybody in congratulating Madam Chairwoman on her retirement and thank her for the years of service that we have shared together and all that I've learned. I wanted to start with Dr. Kelleher to talk a little bit about the decisions that go into where to locate the manufacturing sites, the factories. I think you mentioned in your early testimony your presence throughout Arizona and New Mexico, and your company and others I know have talked about Texas. I represent the areas outside of Pittsburgh, Pennsylvania, that were long the manufacturing hub for steel and other specialty metals and kind of related industries. And we're doing everything we can to try to bring some of our manufacturing know-how, and particularly our land, which is still very well suited for manufacturing. The old manufacturing sites have not all been turned into anything else, and they're still sort of sitting there waiting to be taken advantage of. And I just wonder if you had any insights for regions of the country like mine to talk about what competitive advantage did you see in the Southwest, and how could we maybe look to match that or exceed it in a part of the country like Southwestern Pennsylvania?
Well, if I speak first of all for the Southwest, our investments began in the Southwest 30, 40 years ago. So I will and once you started an investment on a given site, you tend to continue to grow that investment within the site, given the level of infrastructure that you have made. So I'll speak more generically in terms of our overall site selection process. What we look for when we're doing, we have a very stringent criteria from looking at from our site selection. We look at the basically the for the given sites that become available in any given state. We look at basically the land itself, right? And there are many factors you need to take into account when you're building a factory in terms of the site readiness. It's infrastructure. It's basically the availabilities of utilities and infrastructure. It's also what is the supply chain support in a given area, and are you starting the supply chain support from scratch? It's also what is the workforce available in a given area. And what is the availability from anywhere from unskilled workforce to the skilled workforce. And also there is a look at in terms of the overall, I would say the given states in terms of their how much they work with business, so that it becomes easy to do business in a given state. So there's an entire set of criteria by which we work through as we make our selections.
I really appreciate that. And I see us having a fair amount of advantage on many of those metrics. Supply chain, I don't quite know. That might be one we have to work on. Any other witnesses want to address that? Obviously our connection to Carnegie Mellon really helps with the talent pipeline, but anyone else have anything to offer for Southwestern Pennsylvania and kind of the Rust Belt overall as we look to make the transition?
Well, I think I'll just amplify Dr. Kelleher's comments regarding, infrastructure and workforce. Those are two key elements. The semiconductor manufacturing operations complexity is incredible, and it's continuing to get more and more complex. Fractions of a second of power loss can create significant disruption. And so the utility infrastructure, including electricity, availability of water treatment, all of those are key factors. And then, as she mentioned it, as you're noting, the availability of skilled workforce, whether that's the proximity to top universities or vocational schools and community colleges that can help us with the training and reskilling of technicians to work on this highly precise equipment. These are all the areas that we think about. And then just overall an industrial backdrop and an ability to have delivered industrial success stories over time and the know-how to be able to do it. Because when we make these decisions, they're not 5-year decisions or 10-year decisions. They're 30 or 40-year decisions, as Dr. Kelleher also noted.
Right. Well, thank you very much. I think I'm out of time, but we have all of that in Southwestern Pennsylvania. So all of you listening right now, please keep us in mind in the future. And I very much appreciate your joining us for today's hearing. Thank you. I yield back.
Mr. Kildee is recognized.
Thank you very much. And at the risk of being repetitive, I just want to say what a great opportunity it has been for me to serve and will continue to serve for the next year or so with Chairwoman Johnson. She's been an incredible leader. And as has been said, the example that both the Chairwoman and Ranking Member Lucas have set is an important example. I think that the rest of Congress would do well to heed. We do have our differences, but we work them out in, I think, a mostly civil manner, and that's really important. So thank you. And thanks for holding this hearing. I recently welcomed Commerce Secretary Gina Raimondo to Michigan for a discussion on the global semiconductor shortage with auto workers, with business leaders, with other elected officials. And as we know, while the semiconductor shortage is affecting a lot of industries, it is disproportionately affecting the automotive sector, impacting thousands of workers that I represent in my home district. We've seen layoffs at General Motors Flint assembly plant over the summer, and some of our factories in Flint have been idled, in Michigan, I should say, have been idled since the spring. And that's why I've been working with others in the House to invest in legacy chips that are commonly used in automobiles. And I know this has been the focus of this hearing, and it might be somewhat repetitive, but I want to make sure we get as much information on this as we can. We obviously have to get serious about strengthening our domestic semiconductor supply chain. And we have to act now to save American jobs, to ensure a robust domestic automotive manufacturing industry here in the U.S., not in other places. So if I could start, Mr. Bhatia, in your testimony, you advocate for the U.S. to focus on leading edge manufacturing capabilities, which makes sense, to maximize the commercial success of our investments. But as we know, these cutting edge fabs and foundries will take quite some time to build, as you've mentioned, even if we immediately fully fund the CHIPS Act. So here's the question: how can we leverage the existing infrastructure today across industry to kickstart manufacturing advances while we wait for these fabs to be built? And what can we do in Congress specifically to address that issue?
So thank you, Representative Kildee. And, First, let me just echo your comment that we need to move with urgency now. To me, even though it will take years for the CHIPS Act funding and investment tax credits to improve the domestic supply chain for semiconductor manufacturing, we do need to move urgently, and we need to get started now because other countries around the world are not standing still either. So whatever gap exists today, the gap is only growing until we actually are able to start reversing that trend. And let me also agree that automotive is an incredibly important market for all semiconductor manufacturers, but for Micron as well, we're the number one provider of memory solutions to the automotive industry globally. What we have tried to do with this, and one of the things that we've been successful in to ensure that memory has not been one of the primary bottlenecks for the automotive industry, is working with our customers to move them towards newer technologies. And this is an area where closer collaboration between the semiconductor manufacturer, the system design houses, and third parties, as well as the tier one OEMs together, to be able to make a concerted effort to qualify newer technologies, because investments, whether they come spurred by the government or from industry, they will always lean towards the future and towards leading edge. And so in order to really future-proof, what we've been working with our automotive customers to do is to get their engineering resources dedicated towards newer technologies, because if there are requirements they need, we can focus on those more earlier in the process and be able to get them to newer technologies.
Thank you very much. And just in the last few minute or so, Dr. Kelleher, of course, Intel produces personal electronics computers, but it's also involved in the auto sector. How do we balance the needs of these different industries of both leading edge chips and these legacy chips? What's the approach you take, or you think we should take, in terms of trying to find that right balance?
Well, I concur with what Dr. Bhatia said in terms of at this point, I think working with the auto industry to move them to more leading edge nodes, so that as we invest in the infrastructure, that the infrastructure we invest in actually can help enable that industry for many years to come. Right. So I think the key part of it, and yes, Intel, we're involved working with the auto industry, but the key is to help start moving the auto industry from being in the very much older nodes where many of the equipment doesn't exist anymore to even manufacture it, onto the newer nodes, so that we can continue to keep the auto industry in progression with the rest of the semiconductor industry, so then that we never again get to the point of where we have this level of disparity between the support of the auto industry and the rest of the industry.
Thank you very, very much. I see my time has expired. I thank all the witnesses for your excellent testimony. And Madam Chair, thank you for this hearing. I yield back.
Ms. Ross is recognized.
Thank you. And thank you, Madam Chair, for holding this hearing. And I just want to say, as a freshman, thank you for setting an example of being an outstanding committee chair and of showing civility, working across the aisle, and mentoring the next wave of legislators. So I really appreciate all that you've done. And I look forward to working with you the next year as we do even more. I also want to thank the panelists for joining us today. As we've been hearing, these pandemic-driven shortages of semiconductors have revealed how dependent the U.S. economy is on foreign suppliers. And it's not just in semiconductors, it's in so many other things in our supply chain. But we've seen how essential semiconductors are to so much of what we do. I represent the Research Triangle area of North Carolina, and I've seen in my area how these shortages have hurt our economy and our innovation ecosystem. And right now, I'd like to let you know, if you don't know, in my district, it's the home of North Carolina State University, and where it's a leader in Power America, a public-private partnership between industry, or among industry, government, national labs, and academia, that's accelerating the commercialization of wideband semiconductor technology. And after 5 years of Department of Energy funding, Power America now has 60 members and is completely self-sufficient. it's also spawning people to leave and go into startups. And so the startup economy is very big in the Research Triangle area. But microelectronic startups often find it difficult to commercialize their products. Even well-funded startups struggle to secure time at fabs and foundries to test their products as they compete with larger companies for access. And right now, we need as many people working on this as possible. So Dr. Chiang and Dr. Witherell, how can we grow a semiconductor startup ecosystem here in the United States? And do we have the time for it?
Well, Congresswoman, thank you for the question.
Go ahead.
Please go ahead, Dr. Witherell.
Well, I can say one thing. We have in the laboratories, we have systems for doing startups from the laboratories. We had Cyclotron Road here, and included, we have startups coming out in semiconductor industry that are fellowships that are supported by DARPA now. So there is but I will say to lead to the dean, the university is a much wider space for this, and so we should hear from him.
Please.
Thank you, Dr. Witherell, and thank you, Congresswoman. And indeed, I am confident that Congress and the cabinet, including Secretary Raimondo, will be very comprehensive in the strategies. And we just talked about, let's not forget the legacy nodes that produce a lot of the chips needed, for example, for the automotive industry. We should also not forget the military needs, including workforce. For example, Purdue, these 12 universities working with the DoD in the SCALE, SCALE program for DoD semiconductor workforce development. And this is yet another example that let's not forget that we also have small enterprises, including startup companies. But I think there's a reason why there's a lack of interest compared to other fields, because the time to generate return to the investors tends to be longer for semiconductor companies. Unlike fields such as artificial intelligence or mobile applications, semiconductor chips, especially those at the leading nodes, takes hundreds, not thousands of engineers and hundreds of millions of dollars to go to a mature stage. And most of the investors are not patient enough when there are competing opportunities for their cash resources. So I think part of the solution could be to encourage more of the university industry collaboration, to encourage faculty and students to work with industry leaders and take their patents and take their research articles into the potential translational path so that there's a larger volume of choices for the investors. And part of that is indeed back to the CHIPS Act, to restore a free market balance, not to tip it, but to restore it so that investors will be more confident that there is a vibrant future for their investment in the semiconductors industry in the US. And that's yet another reason why the CHIPS Act funding will be so important, not only to the major players, but also to the upcoming small companies.
Well, thank you very much. And I see my time has expired, so I yield back.
Ms. Moore is recognized.
Well, thank you so much. And of course, I am so pleased with myself that I decided to be on the committee with the Honorable Representative Eddie Bernice Johnson. I would have just killed myself if I hadn't had the opportunity to see her in action, and she is such an inspiration. I am going to sound repetitive, I'm sure, because I want to sort of relate to some of the things that I have heard before. Question really for Dr. Kelleher and maybe Dr. Chiang. I am from Milwaukee, Wisconsin. And of course, this is a place that we were known at one time to be the machine makers of the world. So I'm wondering, Dr. Chiang, when you talked about workforce development and all that, when we start talking about place-based strategies to do things, will this funding enable a place like Milwaukee to have a level playing field by providing funding for training and upgrading, because we have a fantastic workforce for generations that was accustomed to manufacturing? Or are we going to just be flyover country and they're going to run off to California or some of these other places? And so I am very, very, I talked to Deputy Director of Commerce, Don Graves. He indicated he thought that the Midwest would be a great place to do this kind of work. And I'm wondering, if, because Milwaukee's a great place. We've got a port, we've got water. There are deals that can be made with local governments regarding utilities and so on. Is it foolish to even hope that a place like Milwaukee could be a site?
Congresswoman, well, let me share the Midwest enthusiasm that you just expressed so well. And indeed, here in the Midwest, whether it's in Indiana or Wisconsin or any other states here in the middle of the country, we have a lot of customers. And, I hope companies will want to be closer to their customers. We have a lot of talent, and I'm hoping that the workforce development portion of the NSTC in the CHIPS Act will support a nationwide distributed network that accesses diverse talents and is geographically inclusive. And
well, I appreciate that. Listen, I want to yield the rest of my time to Dr. Foster. I can't see my clock, but I would like to yield to Dr. Foster.
Dr. Foster's not present right now.
Oh, okay. Well, I know he was very eager to finish his questioning, and so I wanted to accommodate him. So I will yield back my time.
Thank you. Mr. Pete Meyer is next.
Thank you. And thank you, Madam Chairwoman, for the hearing today and for all of our panelists who are here. I want to second Ms. Moore's comment and just note that I think I haven't been in a private meeting among members or in a committee hearing that has at all touched on microelectronics without all of us making the respective cases for our districts on why they are best positioned. So there is strong support, and I think not only a recognition in how critical this issue is, but also on the opportunities that it presents. And I guess specifically, in Michigan, the semiconductor shortages that we've seen domestically have been dramatically impactful on our automotive industry, and not just on, the big three and the largest producers, but also in all of the constituent industries and manufacturers that are serving in there. As a member of this committee, I've been particularly engaged and interested in this issue of domestic manufacturing, and specifically on semiconductor chips, and how we can support new programs within existing agencies like NIST to advance additional domestic production. I was proud that earlier this year, we were able to secure additional funding for the Manufacturing USA Institute, which passed unanimously in committee, but unfortunately was not included in the final package passed by the House. These dollars would have gone towards research, development, education, training, or domestic semiconductor manufacturing pipeline. And I'm retain some optimism that we'll be able to still complete that, given the number of tasks ahead of us on the committee. I guess my first question would be to Mr. Bhatia. It's my understanding that many experts believe breakthroughs in packaging will really be key to improving chip efficiency beyond the gains already achieved through Moore's Law. Can you share what the role of a federal supported research and development center that's focused specifically on advanced packaging? What could this bring in terms of uniting stakeholders together to tackle this challenge?
Thank you for the question, Representative Meyer. And first of all, I'd like to say that we support the idea that there should be that the NSTC centers should be focused on specific areas and verticals rather than one monolithic center. So a center focused on packaging makes a lot of sense. And where we really see the benefit is as advanced as the scaling of primary logic chips becomes more and more challenging. There is, and as memory becomes a larger portion of the semiconductor ecosystem, the ability to put heterogeneous packages together that combine logic chips from one company and memory chips from another company and possibly packaging technology from a third company together, these are the kinds of breakthroughs that are going to be needed to address both the performance requirements of computing paradigms of the future, as well as power requirements of the computing paradigms of the future. And so, there really can be an important role played for packaging where the number of companies coming together are from different parts of the industry.
And I think that packaging component, with the exception of I believe it was Dr. Foster, a lot of us do not have personal experience within this industry, and it's obviously a highly complex, highly developed one. But I think the role of packaging within microelectronics is, again, one of those limiting coefficients that is vital to the broader semiconductor industry, but sometimes gets a little bit missed when we're talking about it congressionally. And next, Dr. Kelleher, in your written testimony, you had described the advances that international rivals are making in the global semiconductor technology industry. Can you briefly share, what are the consequences of having to import such advanced semiconductors, and what should that ultimate balance look like between domestic production but still having potentially some international supply?
Well, if I look at Intel over the last 50 years, we have done the majority of our manufacturing within the United States. I believe for basically going forward, our aim is to continue to do that. And I believe that going back to, we were talking about supply chain robustness, etc. For the United States, we should have a majority of manufacturing, or basically a significant increase of where we're from today in terms of having our own independence. I'll also look back to your last question, if that's okay, around packaging. Intel has leadership in packaging, and all our IP and development on packaging is done here in the United States. A lot of the packaging right now, other R&D and development work is done in Asia. We truly believe that establishing a center around advanced packaging will continue to help us continue to push the edge and leading on overall packaging and maintaining that leadership, but will also bring the rest of the United States so that we'll be in an ability not just to have the capability of it in the United States, but also the ability to manufacture it in the United States.
Thank you, Doctor. And my time is expiring, but I just want to thank again the chairwoman for holding this, and our ranking member as well. And thank you to our witnesses being here today. I think this is a vital topic, and I hope that we see legislative progress on this in the short term. Thank you so much. I yield back.
Mr. Byer is recognized.
Thank you very much. And I don't want to say goodbye to Chairwoman Johnson, because I'm looking forward to 13 more months of serving with her wonderful leadership. And maybe she'll change her mind. But I do want to wish you a very happy birthday tomorrow, Eddie Bernice. So congratulations. It's wonderful I'm glad you were born. And to move on, Mr. Bhatia, a long time ago, I was Lieutenant Governor of Virginia, and with Governor George Allen, we cut the ribbon on the big silicon plant out in Manassas, Virginia. And Governor Allen said, we're moving on from the Old Dominion to the Silicon Dominion. What happened? How did everything end up in Taiwan rather than in Virginia or in the United States?
Representative Byer, thank you, and thank you for participating in that ribbon cutting ceremony. And our Manassas, Virginia facility continues to operate and provide important supply for the automotive industry and networking industry and other industrial industries. It's actually one of the key parts of our global supply chain network. But what really happened was, I think that event that you're referring to was probably in 1998 or so. Is that about right, roughly? And Micron acquired that site shortly thereafter. But in the middle of that, it began 20 years of concerted policy by Asian countries to build up ecosystems and scale to create favorable environments for semiconductor manufacturing. There also happened to be the transition from the 200 millimeter technologies that have been talked about on this panel to 300 millimeter technology. And that's where Asian countries really focused on making sure they were building up their ecosystems as the industry transitioned in the early 2000s from 200 millimeter to 300 millimeter. And particularly in semiconductor memory, the scaling up of those facilities just provided tremendous economic advantages that the smaller sites in the United States, without the government support, without the ecosystem development, just couldn't compete. And so the Asian countries, particularly around memory, did end up having much larger scale manufacturing and much more cost-effective environments. And this trend over the last 20 years, won't be reversed overnight. I think CHIPS and the investment tax credits that are proposed are a good start, and they are, we need to act with urgency because, as I mentioned before, the gap is only widening because Asian countries, many of them, are already outlining policies for long-term decades of investment with tens or even hundreds of billions of dollars of investment. So we really do need to move quickly. Over time, we can see that this gap closes, whether that gap is in the production output or in cost structure as the scale factors start to come together. But we need to act now, and we need to get about reversing this trend if we want to have leadership in long-term microelectronics.
Thank you. I'm trying to get one more question in for Dr. Chiang. When I talk to my friends at Micron and Intel, they talk about, billions of dollars to get the new plant up. How do we grow the semiconductor startup ecosystem? How do we help the little guys, who are developing all the cool chemistry? I'm sure they're doing when Bill Foster was winning his awards 30 years ago, he was probably doing it in a small lab.
Thank you, Congressman, for the question. And as we have already all observed throughout this hearing, that the semiconductors industry is a large and diverse one, as is our country, the United States. And there are many different components and opportunities. For example, a startup company in the design of chips today will face a different kind of challenges than those focusing on packaging. And there are states whereby the largest mega factories will be located. And there are many other states where smaller fabs, legacy node fabs, or packaging centers might be created. But in general, I would say that as SIA or SRC, these industry consortia have indicated that we need to restore a free market balance, and CHIPS Act will help to accomplish a big portion of that goal. And second is that we need to encourage more students and faculty to work with industry in order to be the co-founders or the first set of employees of these startups. The fundamental root cause, I think, is that most of the investors view the investment into semiconductor startups not as potentially high return as some of the other startup investment opportunities. So restoring the market balance and increasing the volume of the deal flow would help to tackle those challenges for the startups.
Thank you very much. And Madam Chair, I yield back.
Mr. Obernolte is next.
Thank you very much. And thank you to our witnesses for what's been a very fascinating and impactful hearing. My first question is for Dr. Kelleher. In your testimony, you discussed the fact that we have a 30% cost disadvantage in attempting to do semiconductor manufacturing here in the United States versus overseas. I wonder if you could just tunnel down on the cost drivers for that 30% difference and what can be done to restore U.S. competitiveness in that area.
I'll break it into probably three portions, right? First of all, there's a labor cost difference between Asia and the United States. Second of all, the cost of building and the cost of building the fabs in Asia is less expensive than in the United States. And third, there is the incentives which are available within Asia for many of the countries are also make it so that the combined of those three together is what gives the 30% cost disadvantage. So the work that's going on here through the CHIPS Act in terms of how it will potentially help us as we go in our industry not just from for R&D development, because that it has also the same cost disadvantage because it's done in the fabs by researchers. It will help to address the cost disadvantage against those which is made within Asia, and actually gets us to be in a place to be more competitive.
Okay, I'm sorry. The last thing that you said, could you say that again? Because that was going to be my next question: is what do we do? What can government do to help bridge that gap?
I think there's two pieces. I'll break it down into. First of all, there is within the CHIPS Act, moving forward with the CHIPS Act and supporting and particularly in the NSDC, and basically consistently and having a structured framework to fund into the R&D within the United States, and then the greater CHIPS Act in terms of enabling leading edge to be able to build out it's basically the manufacturing of the leading edge technologies. So the CHIPS Act is absolutely key in terms of working and basically enabling that to come into play so that it enables the industry to be able to start eating into that cost disadvantage.
Okay, so maybe you can tunnel down on this a little bit further, because I see this as two different problems, right? There's the problem that we are in danger of losing our position as the world leaders in the technology, and that's certainly something that we can catalyze a solution for. But then there's a separate problem that most of the manufacturing is not done here in the United States anymore, which has national security implications for us. So we want to see more of those fabs here, and not just the fabs for the last generation of technology, but the fabs for cutting edge technology be here. So I see the CHIPS Act. I see how what you're saying is true for solving the first problem, but I don't see how that reduces that 30% cost disadvantage that's preventing those fabs from being here in the United States.
I think through the CHIPS Act, in terms of the incentives from the United States government, that will start eating into that differential. And ultimately, the choices where companies go to make to choose where they build their fabs it goes back to what are the incentives available for a given country, as well as what is the supply chain and the people and the skills and all of that. But the funding coming through in the CHIPS Act will start helping to turn the tide and start eliminating the erosion of the manufacturing going off-site and start bringing it back on-site to the U.S.
Okay.
Representative Oberhalti, can I add a comment?
Sure, go ahead.
Sure. I just want to just add one data point, just so that it's a Micron-specific data point, but it's very common across the industry. The capital intensity of our industry, particularly memory, is tremendous. Micron will spend more than 30% of its revenue back in capital again every year. And so in addition to the CHIPS Act, an investment tax credit that refunds capital investment is a really key element to make sure that we can start to close this. Micron sees 35 to 45% cost gap with much larger scale operations that are already in place in Asia for our competitors.
Right. I think we are in complete agreement on that, but it would have to be very targeted. And I'm not sure what you have just described is sufficiently targeted, because, we're kind of at cross purposes where industry is pursuing, the commercial incentives, where we in government have a national security justification for wanting those fabs to be here. So it does us no good if, we catalyze further development in cutting edge technology if that technology is still manufactured and deployed in other countries. We need to solve both problems. But it's a fascinating discussion. I think that what you're hearing on the committee is a willingness to work with industry and trying to solve both of those. So I want to thank our witnesses, and I'll yield back.
Mr. Jimenez is recognized.
Thank you, and a happy early birthday to the chairwoman. I want to thank you for this hearing, and also to our ranking member. Thank you. I've got 2 or 3 questions for Ms. Kelleher. Is it true that Intel is planning to build new facilities, new manufacturing plants in China?
So Intel and the US government, we share a goal of addressing basically the ongoing industry-wide shortage of microchips, and we have explored a number of approaches with the US government. However, our key focus is on the significant ongoing expansion of our existing semiconductor manufacturing operations, as we have already announced, which work is ongoing in Arizona and New Mexico, and we're working on selecting a greenfield site here in the US and in Europe. This will take time, and again, I urge Congress to fund the CHIPS Act so we can accelerate the progress here in the US. Given the urgency of the shortage, we remain open to other solutions that would help meet high demand for semiconductor essential to innovation and economy. But basically, we...
Ma'am, I've only got a certain amount. Is it a yes or no?
So I'm not going to discuss specific business discussions with the US government here.
Okay. So, do you view China as a competitor, or do you use it? Do you view it as a place of it's an opportunity or a competitor? What do you view China as?
China is part of our world market, but I also am very clear around protecting my IP from a technology's perspective here in the United States.
Okay, so I would take that the answer is that you view it as an opportunity. It's part of the world market. Do you intend to seek grants from CHIPS if it is passed? Given
Intel is the leading manufacturing leading edge technology here within the United States, and we have had long investment history here in the United States.
I'll take that. I'm sorry. I'll take it as yes. Again, I've got some questions and I really need to go. So I'll take that as yes. Okay, you're gonna seek funding from CHIPS. All right. We talk about when you talk about a supply chain, you have the chips themselves, but then what the stuff that makes the chips. All right. And so the testimony says that the rare earth minerals, all these minerals that go into making the chips, they're actually a lot of them come from China. Does the United States have the capacity? Does it have the resources, the natural resources to produce this in the United States?
I think all of it, I don't believe, yes, that there is, but this is an ongoing work that different parts, I know Dr. Bhatia said Micron is working with the United States and Intel is also working with the US government, because this is a piece of work that to robust the supply chain that we have quite a bit of work to do.
And is it because of regulations, et cetera, that we're not producing this stuff here in the United States? Is it because of us? We're doing something wrong here, Congress, the executive branch is doing something wrong so that we don't incentivize that production here in the United States? Because actually, if we bring all this manufacturing back and we still don't have the supply chain for the chips themselves, we're not going to be anywhere, right? We need to have it all basically here. Would you agree with that?
Having basically a significant portion of the supply here in the US absolutely will help, right? Your question in terms of, is it something legislation is doing? I would put it more that I think it needs to be a raise in the importance in terms of within the supply chain. And I think once it raises within the importance of the supply chain, then the might of the entire industry works in it to get a better answer.
Is there any research going on into creating chips that don't need these materials and need something which is abundant or not quite as expensive, maybe not quite as exotic? Is there research going on into creating a cheaper chip that's just as good or better than what we got right now?
If you go back to say some of the core ingredients of the advanced materials that we use today, I think one of the key aspects of within NSTC and research of the future is how do we replace those with alternate materials? I mean, the periodic table is actively being used in terms, and as we advance the technology, we typically end up using new element, or basically more elements of the periodic table. So I think one of the things I would like to see out of NSTC is an ongoing activity in terms of how we actually move ourselves to be from less dependent on some of those materials. And then,
right, and I know that my time is up, and my final comment would be that we would, hopefully the United States would be helping you develop those materials that would make us less reliant on outside sources to create these chips. And thank you so much. And again, I yield back. Thank you.
Mr. Waltz is recognized.
Hey, thank you, Mr. Chairman. And just to build on my colleague from Florida, Mr. Jimenez's, I thought, very thoughtful and timely questions on the supply chain and on critical minerals. I've often spoken about and worked on legislation in the Defense Department, on the Armed Services Committee for the Defense Department, trying to address the United States' heavy reliance on China for access to critical minerals. The Chinese Communist Party has openly threatened Japan, Australia, and others with withholding these critical minerals as part of, in line with their geopolitical interests, and frankly, in line with the dictatorship that the CCP is. So I've introduced HR 2637, the American Critical Mineral Independence Act. It has a number of provisions to support research and development. Dr. Witherell, can you speak to what it would mean for the semiconductor industry to be able to understand and control minerals and to manufacture them, and to be able to process them? The role DOE labs like Berkeley National Laboratory and others play in making this the reality, and to directly address Representative Jimenez's questions, I think we need to have an honest conversation about our own rules in terms of mining on federal lands, in terms of NEPA and our environmental restrictions, the fact that it takes on average a mining company in the United States 7 to 10 years to get an appropriate license. In Australia, it's 2 to 4 years. So I think this is an interesting kind of academic conversation here, but we're not being honest with ourselves about our own restrictions that we put on being able to control our own supply chain. I can tell you, sitting on the Armed Services Committee, we are losing badly. If you look at the trend lines of what the Chinese will be able to control and what we're giving up. In fact, Build Back Better, the House just passed, will close down America's largest copper mine because it's on federal lands. So, Dr. Witherell, can you speak to how critical this will be to able to control the critical mineral supply chain?
Well, there's enormous effort across the DOE laboratories on critical minerals and materials, and on developing, and it's everything from, and of course it's broader than semiconductors, batteries too, cobalt for batteries and other things. And we're working on developing, number one, thinking about the new technologies, being able to use minerals that are not as rare so that we can actually build them. At the same time, there are efforts on how to get lithium in this country, how to get other minerals in this country. And that's going to be, I think, an increasing emphasis among the DOE laboratories in the future.
Well, no, thank you. I appreciate that. And, it's interesting. You mentioned lithium, which is obviously critical for battery manufacturing, which is critical for a green economy, which many of us support. However, I don't want to increase our dependency on our greatest adversary as the cost of having a green economy. It's also worth noting that in Afghanistan, we had the world's second largest known lithium reserve, third largest copper, fifth largest cobalt. And we just handed that over to the Taliban, who are now actively flirting with Chinese mining companies to exploit those resources. Dr. Kelleher, so the mistakes that we inflict on ourselves, and that frankly this administration's policies are inflicting on this entire effort, again, is something that I think we need to have an honest conversation about. But Dr. Kelleher, I wanted to, again, I know you've been asked, and I apologize if I'm repeating here. I applaud the investments made and that you're looking to make in the United States. I am concerned about Intel's plans to expand manufacturing in China. And I know you talked about the cost differential. We know much of that is subsidized by the CCP in terms of creating that differential. But again, sitting on armed services, we are pulling our hair out trying to keep up militarily with Chinese investments, and then to watch American companies continue to invest there. I understand the cost differential of the United States, but we also have, we can make investments into India. Happy to help you with that. We can make investments into Vietnam, and there's kind of allied shoring in addition to onshoring. So can you talk to those efforts
So some of we have manufacturing facilities within Vietnam. We have also manufacturing facilities within Malaysia, and we have also manufacturing facilities within Costa Rica.
Just in the interest of time, ma'am, I don't mean to cut you off. I'm just out of time. Why are you expanding in China then, rather than those other facilities?
I didn't say we were expanding in China. I was very clear what we have announced is expansions here in the United States, and what we have formally announced is expansions here in the United States and in Europe. What I did say is I wasn't directly to the question that that I got asked earlier is versus discussions with the US with respect to China, and I said bottom line is I'm not discussing that.
Okay, well, there's just been reporting of your expansion in a Chengdu factory there that the Biden administration has expressed serious concern about. I think that's what I was getting at. If you could send an answer for the record, I'd appreciate it. Thank you, Chairman, for your indulgence.
Thank you very much. I think that is the end of our witnesses. But before we bring this hearing to a close, I want to thank our witnesses for testifying before the committee today. The record will remain open for 2 weeks for additional statements from the members and for any additional questions the committee may ask of the witnesses. The witness is now excused and the hearing is adjourned.